For millions of years, a single star holds itself perfectly still, not through rigidity, not through the hardness of stone or the cold patience of iron, through light, through the constant outward push of light born from hydrogen fusing in its core, a pressure rising against gravity in a balance so precise, so sustained across such an unthinkable span of time that to a distant observer the star would appear simply to hang in the dark, motionless, a fixed point of fire in a sea of other fixed points, betraying nothing of what it carries inside. That balance is the beginning of everything that follows, and the following takes a very long time. A massive star, one born with more than roughly 8 times the mass of the Sun, draws on a particular kind of hydrogen burning deep in its core. Not the slow proton by proton chain that powers smaller stars, but a cycle that runs hotter and faster, threading carbon and nitrogen and oxygen through the reaction as catalysts, cycling back to the same elements it began with, using them over and over while hydrogen is consumed and helium builds in the core. This is the CNO cycle, and it operates at temperatures tens of millions of degrees above what the Sun maintains in its own center. A star burning this way may sustain its balance for 3 million years, or 30 million, depending on its mass. The more massive the star, the faster it burns, the shorter its main sequence life. But even 3 million years, set against the scale of a human life, or a civilization, or an ice age, is a duration so vast that nothing within it seems to move at all. The star hangs, the light pours outward, gravity pulls inward, neither wins. The star is not inert, though. Deep inside, the core is consuming itself, one hydrogen nucleus at a time, building helium as it goes, a slow and irreversible drift toward the moment when there is no hydrogen left to burn. That moment does not arrive dramatically. It arrives as a quiet diminishing, a gentle lessening in the energy released per second, a slight contraction as the outward pressure fails to match the inward weight, and then the core contracts, heats, and finds a new source, helium now, fusing into carbon and oxygen. The outer layers respond to this new pressure from below, and they begin to move outward, not quickly. Nothing in stellar evolution moves quickly. Over thousands of years, the outer atmosphere expands, cools, and reddens. The star swells. It becomes a red supergiant. If a red supergiant of this kind were placed at the center of our own solar system, at the position of the Sun, its surface would extend outward past the orbits of the inner planets, past the asteroid belt, past Jupiter, and the wide, slow arc of that great planet's path around the Sun. The star's outer layers would reach to where Jupiter now traces its orbit, swallowing everything inside. Earth would lie within the star's atmosphere. Mars would be gone. The gas and the glow of that outer envelope would hang where Jupiter now circles, and beyond the star's edge, the outer solar system would continue as before, undisturbed. This is not a metaphor for scale, it is a literal displacement. The star has grown to fill what we know as the inhabited interior of our solar system, and still, at its center, the burning continues. After the helium in the core is exhausted, the core contracts again. Carbon burning begins, with temperatures now in the hundreds of millions of degrees. This stage lasts hundreds to thousands of years. When carbon is depleted, neon burning follows, and then oxygen burning. Each successive stage runs faster than the one before, because the more advanced the fuel, the less energy it releases per reaction, and so the star must burn more rapidly to maintain itself. And inside the contracting core, the burning stages that have already finished do not disappear. They persist as completed shells, layered around the current burning zone, each one a record of a stage already passed. This is the structure a massive star builds inside itself, quietly, across its millions of years of life, a system of concentric shells, each one composed of whatever fuel was burning at that depth, before the burning moved inward. At the outermost edge, hydrogen, still fusing in a shell around the helium layer, then carbon, then neon, then oxygen. At the innermost active shell, silicon, burning at temperatures near 4 billion degrees, fusing into the elements of the iron group, the heaviest nuclei that stellar burning can build. These shells are not sharply bounded like the rings of a tree. They blend and interpenetrate at their edges, and the star's internal life is complex and convective and turbulent on small scales. But the general pattern holds, layers of completed history surrounding a center still at work. Each of these burning stages compressed something essential about time. Hydrogen burned for millions of years, helium burned for perhaps 100,000. Carbon burning lasted a few thousand years, neon burning perhaps a year, oxygen burning a few months, and silicon burning, the final stage, the innermost fire, begins at temperatures approaching 4 billion degrees and runs for days. Only days. In that brief interval, silicon nuclei in the core fuse in rapid alpha capture reactions, building steadily upward through the periodic table to sulfur, argon, calcium, and then to the iron group elements, primarily an isotope of nickel, nickel 56, which will later matter enormously for reasons having nothing to do with what is happening here. The entire silicon burning shell converts to iron group nuclei within a human week or two. The burning stage that took hydrogen millions of years to complete is here compressed into an interval shorter than a season. What silicon burning leaves behind is an inner core of iron group elements, and this is where the long patience of the star's life meets its structural limit. Iron is the end of the road for fusion as a source of energy. Every element lighter than iron releases energy when fused with another nucleus. Every element heavier than iron absorbs energy rather than releasing it. This is because of the shape of the nuclear binding energy curve. Iron and its neighbors sit at the peak, the point of maximum binding per nucleon, where nuclear reactions cannot provide any more. A star that tries to fuse iron to release energy will find only silence. The iron core that silicon burning has assembled cannot be a fuel. It can only accumulate, and it does accumulate, growing heavier with each passing day as the silicon burning shell above it continues its work, raining iron group nuclei down onto the core below. The core grows, and as it grows, the mechanism that supports it against gravity must work harder and harder to maintain its hold. That mechanism is not heat. The iron core does not burn. It does not radiate energy outward from its own reactions. What holds it up is something more fundamental and more subtle, a quantum mechanical pressure that arises from the nature of electrons themselves. Electrons, like all particles classified as fermions, obey the Pauli exclusion principle. No two electrons can occupy the same quantum state at the same time and place. In the extreme density of the iron core, densities far beyond anything achievable in ordinary matter, the electrons are packed so tightly that the exclusion principle becomes a structural force. The electrons resist further compression, not because of heat or temperature, but because they have nowhere left to go. This is electron degeneracy pressure. It holds the iron core up. Millions of years of burning have led here to a quantum mechanical standoff between gravity and the exclusion principle itself. What makes this balance precarious is that electron degeneracy pressure, unlike thermal pressure, does not respond to temperature. A ball of gas supported by heat can be compressed until it gets hotter and pushes back harder, but a degenerate core cannot do that. If it is compressed, it does not grow hotter in a way that restores equilibrium. And more critically, there is a maximum mass beyond which degeneracy pressure simply fails. This is the Chandrasekhar limit, approximately 1 and 4/10 solar masses. Below that mass, a cold degenerate core can hold itself together indefinitely. Above it, even the quantum pressure of electrons cannot resist the weight of what sits on top of it. The Chandrasekhar limit is the precise threshold where the universe's rules will no longer permit the iron core to hold. The core grows toward it, slowly, as silicon burns above. The stillness of this interval is worth holding for a moment. The star, seen from the outside, gives no sign of what is happening in its center. A red supergiant hangs in space with its vast extended atmosphere, its surface temperature low and red, its slow convective cells rising and falling over intervals of years. It has been visible, perhaps, across the spans of time during which nearby civilizations formed and changed. It is old and large and quiet, and deep inside it, an iron core the approximate size of Earth, roughly 6,000 to 8,000 miles across, accumulates mass, approaches a limit, and holds. The core that holds in this way contains, packed into that Earth-sized volume, more mass than the entire Sun. The Sun, with all its hydrogen and its convective turbulence and its 8-minute light travel time, contains less matter than this small, cold, crystalline sphere at the heart of the dying star. The density at the iron core's center exceeds 100 million tons per cubic centimeter, material compressed far beyond anything iron in ordinary experience could represent. It is a sphere of quantum pressure, not burning, not convecting on large scales, just held, just balanced, just enough. The silicon burning shell above it has days left, perhaps a few weeks. Each day it converts more silicon to iron and nickel, thickening the core below. The Chandrasekhar limit approaches in a way that cannot be reversed. No new burning stage waits to begin after this one. There is no deeper fuel the star can reach for. The periodic table ends here, at the iron peak, and the star has climbed it all the way. When the core finally approaches that critical mass, two processes begin to undermine the electron degeneracy pressure that remains. At temperatures approaching 10 billion degrees, temperatures that exist in no other natural place in the universe, on a sustained basis, the photons that fill the core carry enough energy to do something that lower energy photons cannot. They are absorbed by iron nuclei directly, splitting them apart. Iron nuclei, each one the product of 1 billion years of stellar alchemy, assembled element by element across the long history of the star's burning, are torn back into their components. Helium nuclei and free neutrons scatter outward from the disintegration. This process is called photodisintegration, and it absorbs enormous quantities of energy, draining the very pressure that holds the core up. At the same moment, something else happens. The electrons that provide the degeneracy pressure are captured by protons in the iron group nuclei, a process that converts them along with the protons into neutrons and releases neutrinos. Each capture removes one electron from the degenerate sea. Each capture weakens the pressure slightly. The neutrinos, nearly massless and interacting barely with anything, pass outward through the stellar interior and carry their energy away, draining the core further. The two processes, photodisintegration and electron capture, together pull the rug from beneath the iron core's feet. The pressure that has balanced gravity for all of this falls suddenly away. In under half a second, the inner core enters free fall. At a quarter of the speed of light, the inner core collapses. There is no resistance. There is nothing left to push back. The iron core, which has been held in stillness by the exclusion principle for perhaps days or weeks since silicon burning began, and which represents the distilled product of millions of years of stellar burning, falls inward at a speed that would cross the distance from the Earth to the Moon in something like 3 seconds. Everything that the star built across its entire life is now converging on a point smaller than a city in less than a heartbeat. Outside, in the great cold extended atmosphere of the red supergiant, nothing has yet changed. The star still hangs in space. The light from its surface, the slow drift of its outer convection, the ancient glow of its photosphere, all of this continues as it has for millions of years. The light from the collapse has not yet reached the surface. Sound waves from the collapse and interior have not yet traveled outward to the outer layers. For the moment, the star's exterior is exactly as it was. It has not yet learned what has happened at its center. It will not learn for many hours, but the center has already changed forever. The iron core that stood in stillness, balanced by quantum pressure at the precise edge of its structural limit, is gone. Where it was, a sphere of collapsing matter falls inward at a quarter of the speed of light, hurtling toward densities that no ordinary iron can reach, into conditions that no burning stage produced and no equilibrium ever maintained. The collapse has begun. It cannot be undone. What was held has been released, and the star's long history, the hydrogen that burned for millions of years, the helium that followed, the carbon and neon and oxygen and silicon, all of it stacked in shells inside the supergiant's vast body, is now falling toward a single point with the accumulated weight of more than a solar mass, surrendering its long balance to whatever waits at nuclear density. What waits there is beyond the scope of this moment, and the story of what happens next belongs to the instant of the bounce and the wave that follows. For now, the iron core falls. Small and dense and silent, it falls inward through the star's own heart. More massive than the sun, no wider than a small planet, held for so long by a quantum principle, and now released from it in the fraction of a second, the supergiant outside glows on, red and vast, unaware. The balance that sustained it for millions of years has gone. The iron core hangs at the edge, and then it does not hang at all. It falls, and everything that built it across the long and ordered centuries of stellar life, the hydrogen that fused in the CNO cycle at temperatures tens of millions of degrees, the helium that swelled the outer layers into a red giant spanning the width of Jupiter's orbit, the carbon and neon and oxygen and silicone that burned in their concentric shells in stages of decreasing years, the iron group nuclei assembled in the final days of silicon burning at temperatures no other natural process in the ordinary cosmos can reach. All of this converges inward, now pouring down through the star's own geometry toward the center, toward the collapse, toward the density where even neutrons must decide what they will do when nothing ordinary is left to resist the weight of a star that has finally spent itself. The red supergiant, seen from outside, still burns. It will burn for hours more. But at its heart, the stillness that lasted millions of years has ended, and what comes next arrives in milliseconds. For a long time before that ending, for millions of years, across the whole span of hydrogen burning, and the slower burn of helium, and then the faster and faster stages descending through carbon and neon and oxygen to silicon, the star existed in a kind of vast, unhurried permanence. It did not appear to change. Stars on the main sequence are among the most stable objects in nature, their equilibrium self-correcting over short timescales. If the core produces a little more energy and begins to expand, the expansion cools it and the burning rate drops. If the core cools a little and contracts, the compression heats it and the burning rate rises. This feedback is gentle and automatic and built into the structure of thermal pressure. The star breathes, imperceptibly, on timescales beyond any human frame, but it breathes, it adjusts, it persists. To a civilization watching from a neighboring star system for 10 million years, the supergiant would appear fixed, its light unwavering on any timescale a civilization could measure. Its hydrogen supply, so vast and its burning so steady that no meaningful variation would be visible from the outside. And yet inside it, across those 10 million years, the burning was consuming itself irrevocably, moving through its fuels one by one, building the shell structure, assembling the chemistry that would one day be distributed into space. The star looked still. It was never still. It was eating itself in the most orderly and patient way possible, and from the outermost hydrogen envelope to the innermost silicon shell, it was constructing, layer by layer, the compositional legacy of its own death. That legacy is precise. Not in the sense that every atom ends up where a calculation would place it, but in the sense that the physics determines the outcomes within tight ranges. The C&O cycle in the hydrogen-burning core produces helium in specific proportions. Helium burning produces carbon-12 and oxygen-16 in ratios sensitive to a particular nuclear resonance that happens to place their balance at a value favorable to life, a coincidence of nuclear physics, noticed in the middle of the last century, when a physicist calculated that if the resonance were slightly different, the universe would be made almost entirely of carbon or almost entirely of oxygen, and neither outcome would produce the chemistry that builds planets and organisms. The resonance exists, where it does, for reasons that have nothing to do with any purpose. It simply is where it is. Carbon and oxygen therefore coexist in the proportions they do throughout the universe because of a number fixed at the universe's formation that happens to land in a narrow range. The deeper burning stages are similarly precise. The ratio of neon to magnesium emerging from carbon burning, the specific mix of sulfur and argon and calcium produced in oxygen burning, the exact proportion of nickel-56 to other iron group isotopes assembled by silicon burning. Each of these is determined by nuclear physics, by temperature and density, and the timescales over which the reactions proceed. These are not arbitrary outputs. They are the product of physical law operating at temperatures and densities that the star's internal evolution produces, according to the same laws of gravity and pressure and quantum mechanics that govern it from the outside. The star is a machine, in a sense, but a machine so large and so old that its output can be measured not in grams, but in solar masses, and its operation not in seconds, but in millions of years. This is why the shell structure matters. Each shell is a record of a particular set of conditions. The helium shell surrounding the iron core and the silicon and oxygen burning zones holds carbon and oxygen in proportions that reflect the temperature at which it burned and the density at which it was compressed. The carbon shell above it holds neon and magnesium in proportions reflecting carbon burning conditions. Each layer is chemically distinct. Each layer, when the star eventually explodes, will be thrown outward and mixed into the interstellar medium, carrying those proportions into the diffuse gas from which future stars and planets form. The shell structure of a dying star is not merely a curiosity of stellar astrophysics. It is the mechanism by which elements are portioned out to the cosmos. But all of this is still in the future as the iron core falls. The shells are intact. The record they carry has not yet been released. And the star that built them across its long life does not know it has already lost the only thing that kept it whole. The iron core falls, in the dark, in silence, the deepest silence, the silence of matter, under conditions that produce no light, that cannot be observed, that only becomes visible after the fact, when the explosion has already happened, and the remnant has already formed, and the shock wave has already passed through all the shells that carry the star's chemical history outward into space. What sits at the center of the red supergiant in these last moments is an object smaller than any planet and more massive than the sun, supported by the quantum refusal of electrons to share the same state, approaching the precise limit at which that refusal is overwhelmed. It has no burning left. It has no future that preserves it. The silicon shell above it continues to work, adding mass, pushing the core closer to its limit, converting the last of its fuel into the iron group nuclei that fall down to join what waits below. At the Chandrasekhar limit, at 1 4/10 solar masses, the threshold beyond which electron degeneracy pressure cannot hold, the core sits in its last stillness. Not the stillness of a thing at rest, but the stillness of a thing at the very edge of motion, the way a stone sits at the top of a slope before the friction that holds it finally releases, and then there is no going back. In the core of this old and enormous star, in this final moment before the collapse begins, in this last breath of a structure that took millions of years to build and will take under a second to destroy, the electrons hold their positions one last time, and then the photons arrive with enough energy to split the iron apart, and the electrons are captured, one by one, draining the pressure away, and the collapse begins, inward, at a quarter of the speed of light, silent and total and final. The red supergiant still glows outside, in the cold of space, red and vast and old. It does not yet know what has happened at its center. Its light continues outward in all directions, a sphere of photons that set out from the star's surface 8 minutes ago, 10 minutes ago, a year ago. The star looks like what it has always looked like, a point of light, ancient and steady, one among the many fixed stars. And at its center, the iron core falls. At the center of a collapsing star, in a sphere smaller than a city but carrying more mass than the sun, the inner core has reached a density that matter almost never achieves anywhere in the universe. The pressure there is something beyond compression, beyond the ordinary squeezing of gas or the crushing weight of mountains. It is the pressure that exists when atomic nuclei are packed so closely together that they begin to touch, when the particles inside them push back, not through heat or motion, but through the fundamental rules of what particles are allowed to do. And then, in a fraction of a second, too brief to name in any ordinary way, the inner core stops falling. It does not slow. It does not gradually resist. It stops, and then it rebounds. The nuclear matter of the inner core has overshot its equilibrium, compressed past the density at which neutrons and protons can be pressed any further, and the repulsive part of the force that holds nuclei together, the same force that normally operates only across distances smaller than a proton, reasserts itself across the entire compressed core at once. The core stiffens in an instant. What was falling inward at a quarter the speed of light reverses direction, not smoothly, but with the force of a collision between the density of nuclear matter and the momentum of a star's worth of mass still plunging downward from above. The result is a pressure wave, a shock wave, born at the center of a dying star in the time it takes a heartbeat to begin, moving outward into material that has not yet received any signal that the collapse has ended. The inner core, at the moment of bounce, is perhaps 20 kilometers across. It carries the mass of roughly 1.5 suns, and the shock wave it sends outward is moving through one of the most extreme environments in the observable universe. In falling stellar material, at temperatures of tens of billions of Kelvin, densities comparable to the nuclear matter it just left behind, all of it still accelerating inward as the shock tries to push through it outward. For a few milliseconds, the shock moves fast. It travels through the inner core, through the still collapsing outer core, and for a brief interval, it looks as though the explosion might simply happen, that the rebound alone might be enough to blow the star apart. The outward wave and the inward material collide continuously, and for those first few milliseconds the shock is winning. Then the losses begin. The shock passes through the iron-rich material of the outer core, and as it does, the temperature it carries is high enough to undo what the star spent millions of years building. Iron nuclei, the ash of every burning stage the star ever completed, are photodisintegrated. Gamma-ray photons produced in the intense heat behind the shock strike iron nuclei and break them apart, back into the helium nuclei, and free protons and neutrons from which they were originally assembled. This process consumes energy. It costs the shock roughly 7.151 ergs for every tenth of a solar mass of iron it passes through, a drain that does not pause and does not relent. At the same time, the infalling material above the shock is still arriving, pressing against the outward moving wave like a wall of water falling against a fist. The ram pressure of infall adds to the losses from photodisintegration, and the shock, which set out with such force, begins to slow. Within perhaps 100 to 200 milliseconds, well under a single second, from the moment of core bounce, the shock has stalled. It sits motionless at a radius of roughly 100 to 200 kilometers from the center of the collapsing star, not advancing, not retreating, suspended between the material falling inward from above and the energy still arriving from below, a sphere of hot, compressed gas held in an impossible equilibrium, balanced on a threshold that will determine whether the star explodes or whether it collapses entirely into a black hole and leaves no trace but gravity. This stalled shock is one of the central puzzles of modern astrophysics. For decades, theorists could produce the collapse, produce the bounce, produce the shock, and then watch the shock stall and find no obvious mechanism that could revive it. The numbers did not close. The energy budget seemed insufficient, and yet supernovae happen. The stars explode. Something revives the shock. The question was what? The answer, worked out over many decades and still not fully resolved in every detail, involves particles so reluctant to interact with matter that they can pass through the entire mass of the Earth without striking a single atom. When the inner core collapses to nuclear density, the protons that were held in iron nuclei capture electrons and become neutrons, and in doing so, they emit neutrinos, particles with almost no mass and no electric charge, carrying energy outward at nearly the speed of light. Ordinarily, neutrinos interact with matter so weakly that any barrier, no matter how dense, is essentially transparent to them. But at nuclear densities, the matter is dense enough that even neutrinos are briefly trapped. For a short interval, the proto-neutron star that is formed at the center of the collapse is so dense that neutrinos cannot escape immediately. They accumulate, they thermalize, and then as the outer layers of the proto-neutron star grow less opaque, They stream outward in a pulse that lasts roughly 10 seconds and carries an almost incomprehensible quantity of energy. The gravitational binding energy released when a stellar core collapses to neutron star density totals approximately 3 times 10 to the 53rd ergs. To place that beside something familiar, the sun will radiate energy across its entire 10 billion year life, and the energy released in a stellar core collapse in a few seconds exceeds the sun's entire lifetime output several times over. Nearly all of it, roughly 99%, leaves the collapsing star as neutrinos. The visible light, the ultraviolet flash, the shock wave that will eventually tear the star apart, all of it is powered by the remaining 1%. The explosion that will briefly outshine a galaxy of hundreds of billions of stars is, in terms of energy, a small side effect. Most of those neutrinos pass through the entire collapsing star without leaving a trace. They stream outward through the stalled shock, through the infalling outer layers, through the hydrogen envelope of the red supergiant above, and into the interstellar space beyond, moving at nearly the speed of light in every direction, carrying the star's gravitational energy away into the universe, never to be recovered. A thin shell of light will eventually reach Earth, and observers will see a star appear where before there was nothing visible. But of the full energy of the event, almost none of it will ever be detected. The neutrinos will pass through every instrument, every planet, every person in their path, and continue outward forever. A small fraction of the neutrino flux does interact with the material behind the stalled shock. Perhaps a percent or two of the neutrino energy is deposited into a region called the gain region, a shell of material between the stalled shock above and the neutrino radiating protoneutron star below, where the conditions allow neutrino absorption to exceed neutrino emission. In that region, neutrinos collide occasionally with protons and neutrons, transferring energy into the gas, heating it from below. The heating is gentle compared with the full neutrino luminosity, but it is enough to begin destabilizing the stalled shock from the inside. The heated gas in the gain region is buoyant. It rises, cooler, denser material above sinks. Convective plumes form and grow, carrying energy upward toward the underside of the stalled shock, pressing against it from below with the irregular turbulent force of a boiling fluid. The stalled shock, which sat motionless, begins to deform. Its surface, which began as a nearly perfect sphere, develops asymmetric bulges as the convective plumes push against it from below at different places and different times. The shock is no longer spherically symmetric. It is no longer perfectly still. It has become an unstable surface, pushed and pulled by the irregular heating beneath it. And then something stranger begins. The stalled shock, destabilized by convection, becomes susceptible to a large-scale hydrodynamic instability, a collective oscillation of the entire shock surface into modes that are not simple, not symmetric, not spherical. Theorists who modeled this instability named it the standing accretion shock instability. The stalled shock develops lobes, large asymmetric bulges that grow on one side and then the other, sloshing and rotating with a characteristic timescale of tens to hundreds of milliseconds, driven not by local heating, but by the global geometry of the accretion flow. The shock surface, seen from outside, would resemble a vast, slowly churning asymmetric bubble of compressed gas, hundreds of kilometers across, neither stationary nor uniformly expanding, oscillating in a pattern that carries no obvious symmetry. These oscillations matter because they lengthen the path that infalling material takes before it crosses the shock. Material spiraling through a distorted shock spends more time in the gain region. It absorbs more neutrino energy. The effective heating rate rises. And gradually, over hundreds of milliseconds, the balance that had held the shock motionless begins to tip. The energy being deposited behind the shock begins, marginally, to exceed the energy being lost to infoul and photodisintegration. The shock begins to expand. The expansion is not immediate. It is not a sudden release. It is more like the slow giving way of something that has been held at the edge of its tolerance for a very long time. The shock surface grows irregularly, pushed outward in lobes and plumes, some parts of it advancing faster than others, some parts still momentarily retreating, while others surge forward. For a star viewed from the outside, all of this is happening invisibly, buried under tens of solar masses of hydrogen and helium that have not yet felt anything. The stellar surface will not begin to brighten for hours. The photons from the explosion will take time to fight their way outward through the remaining envelope, but inside, the shock is moving again. When the revived shock reaches the oxygen and silicon shells of the star, the layers that completed their burning and were left behind as the star evolved through its final stages, it heats them to temperatures that those shells never reached during the ordinary burning processes that produced them. The shock arrives with temperatures of several billion Kelvin, high enough to drive nuclear reactions that hydrostatic burning could never have achieved. Silicon burning in the core took days to weeks at high temperatures, but it was not instantaneous. The shock heats the oxygen and silicon shells for fractions of a second only, a pulse of extreme temperature, and then rapid cooling as the ejecta expand and the temperature drops. In that brief interval, additional elements form: silicon, sulfur, calcium, and iron group nuclei produced in the explosive version of the same processes that built the pre-collapse shells, but at different temperatures, different densities, and in different proportions. The shock continues outward through the helium shell, which has been sitting quietly, unmixed for millions of years, through the hydrogen envelope, the outermost layer of the star, a vast reservoir of gas that the explosion must push through before it can reach open space. The shock decelerates as it expands into lower and lower density material, but it carries enough energy to keep moving. Days pass. The shock front reaches the surface of the red supergiant, a surface that may be 1,000 times the radius of the sun if the progenitor was a typical red supergiant, and the stellar surface erupts. Light breaks free. At the moment the shock reaches the stellar surface, there is a brief, intense flash of radiation, mostly ultraviolet and X-ray emission, a pulse of photons that had been trapped behind the opaque envelope and are suddenly released as the shock breaks out into space. This shock breakout lasts minutes to hours, depending on the size of the progenitor star. It is brilliant and brief, and it is followed by a longer, slower brightening. The optical display of a core collapse supernova in the weeks and months after the explosion is not powered by the explosion itself. The initial blast has already passed. The ejecta are expanding freely, cooling as they go. What keeps them shining? What sustains the visible glow that allows a supernova to outshine an entire galaxy is the radioactive decay of material produced in the explosion and carried outward in the ejecta. In the innermost regions of the ejecta, close to the center of the explosion, the material is richest in nickel-56. This isotope is the primary product of explosive silicon burning, the most stable nucleus that rapid thermonuclear processing can produce under the conditions inside the shock. Nickel-56 is radioactive. It decays with a half-life of just over 6 days, converting to cobalt-56 through the emission of gamma rays and positrons. The energy released in that decay is absorbed by the surrounding ejecta and converted to heat and light, sustaining the luminosity long after the initial explosion energy would have been exhausted. Cobalt 56, the daughter product of nickel 56, is also radioactive. It decays more slowly with a half-life of roughly 77 days, converting to stable iron 56, again releasing gamma rays that thermalize within the ejecta and emerge as optical light. For weeks after the explosion, the cobalt 56 decay chain is the dominant power source for the visible display. The glowing cloud of supernova ejecta, billions of kilometers across and still expanding, is lit from within by the steady decay of a radioactive isotope forged in the heart of the explosion. The ejecta of a typical core collapse supernova expand at velocities ranging from a few thousand to 30,000 kilometers per second. At the high end, that is about 1/10 the speed of light, fast enough to cross the Earth's diameter in less than half a second. At those speeds, a cloud of ejecta launched at the moment of explosion covers the distance from the Earth to the Moon in roughly 12 seconds. Within days, the ejecta occupy a volume larger than the inner solar system. Within centuries, the expanding shell will have swept up enough surrounding interstellar gas to slow and cool, thinning into the wispy filamentary structures of a supernova remnant. But in the first weeks and months, the ejecta still glow. The glow is not uniform. The ejecta carry the asymmetries of the explosion itself, the convective plumes, the irregular shock revival, the lobes of the standing accretion shock, instability that drove the shock to expand unevenly. The nickel 56 is not distributed in a perfect sphere at the center. It is clumped, mixed outward by the turbulent convection behind the shock, deposited in fingers and filaments that extend further from the center than simple models predicted. As the ejecta cool and thin over months and years, the radioactive material within them continues to power the light, and the spectrum of that light carries within it the fingerprints of specific elements, specific isotopes, specific nuclear reactions. From a distance of several 100,000 light years, that spectrum is readable. The wavelengths of the gamma rays emitted by decaying cobalt 56 are specific, fixed by nuclear physics to particular energies that do not vary. One of the strongest lines falls at an energy of 0, 847 million electron volts. That line, that specific energy, is a signature as unambiguous as a fingerprint. If cobalt 56 is present in the ejecta, decaying as it must, that line should appear in the gamma ray spectrum of the explosion. Astronomers with instruments sensitive to gamma rays searched for it in the light of a supernova close enough for such a measurement, and they found it. The measurement came from a real event, a star that had ended its life in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, near enough that the light of its explosion was visible to the unaided eye. The gamma-ray lines from decaying cobalt 56 appeared in the data precisely when the decay timescale predicted they would, at precisely the energies nuclear physics requires. The evidence was direct. Iron was not carried into the explosion from the star's earlier life. It was forged in the explosion itself, in the shock-heated silicon and oxygen shells, concentrated in the innermost ejecta as nickel 56, and assembled into stable iron 56 through a chain of radioactive decays playing out over weeks in the expanding cloud. This is the connection between the physics of the explosion and the chemistry of the world. The iron produced in that radioactive decay chain did not stay in the ejecta forever. The ejecta expanded, cooled, and eventually mixed with the surrounding interstellar medium. The iron and the silicon and the oxygen and the magnesium and the calcium, all the elements produced in the burning shells and in the explosive shock passage, dispersed into the diffuse gas that fills the spaces between stars. Over millions of years, that enriched gas mixed with older, less chemically processed material. Over billions of years, across hundreds of millions of supernovae from massive stars across the galaxy, the interstellar medium accumulated the elements that no primordial hydrogen cloud contained. New stars formed from that enriched gas. They carried within them, from the moment of their birth, the chemical inheritance of every supernova that had contributed to the molecular cloud from which they condensed. Planets formed in the disk around those stars, small rocky planets assembled from dust grains whose composition reflected the full nucleosynthetic history of the galaxy at the time the planetary system was born. And on at least one of those planets, in at least one solar system in the outer reaches of a spiral galaxy, the iron is everywhere in the core of the planet. In the ancient banded formations of oxidized iron laid down in shallow seas more than 2 billion years ago, in the hemoglobin of every living cell that carries oxygen through a body, in the enzymes that drive the chemistry of life, in the red color of blood. That iron was nickel 56 once. It decayed in the expanding ejecta of a dying star, or many dying stars, releasing gamma rays that heated the surrounding gas. The gamma rays are long gone. The ejecta have long since dispersed, but the iron remains, stable and permanent, carrying no memory of what it once was. There is another path to a supernova, different in nearly every detail. It involves no core, no collapse, no neutron star formed in the aftermath. It begins not with a massive star, living its brief, brilliant life and dying under the weight of its own iron heart, but with a star that has already died, quietly, gently, over billions of years, and left behind a dense crystalline remnant the size of a planet. A carbon-oxygen white dwarf is what remains when a star of modest mass reaches the end of its life and sheds its outer layers into a slow, expanding shell, leaving the exposed stellar core to cool in space. The white dwarf carries a mass comparable to the Sun's, but compressed into a volume comparable to Earth's. At that density, roughly 1,000,000 grams per cubic centimeter, the material is no longer gas in any ordinary sense. The electrons in the white dwarf have been stripped from their parent nuclei and form a dense quantum fluid, while the carbon and oxygen nuclei are arranged in a lattice, crystalline in the oldest and coolest white dwarfs. The whole structure is held up not by heat, not by nuclear reactions, those ceased long ago, but by electron degeneracy pressure alone. The quantum mechanical rules that prevent electrons from occupying the same state hold the white dwarf against its own gravity, perhaps indefinitely. A white dwarf cools slowly across billions of years, dimming from white to yellow to orange to red, eventually fading to a cold dark mass that would be undetectable at any distance, except when it has a companion. A white dwarf in a close binary system with another star finds itself in a gravitational environment where matter can move between the two bodies. If the companion fills its Roche lobe, the teardrop-shaped gravitational boundary within which a star's own gravity dominates, mass from the companion's outer layers flows across the space between them and settles onto the white dwarf's surface. This accretion is slow. It proceeds at rates measured in millionths of a solar mass per year, a trickle sustained across millions of years. The white dwarf gains weight, atom by atom, year by year. The carbon and oxygen in the white dwarf's interior have not burned since the star's red giant phase ended, perhaps billions of years ago. They sit inert, compressed to high density, and maintained at low temperature by the constant loss of heat to space. But as the white dwarf's mass grows toward a particular threshold, the same Chandrasekhar limit of approximately 1/4 solar masses that governs the core collapse scenario, the central density rises, and with it the temperature. At some point, somewhere near the white dwarf's center, the conditions are reached where carbon nuclei begin to fuse. What happens next is determined by a property of electron degeneracy pressure that makes it different from ordinary thermal pressure in a crucial way. It does not depend on temperature. In an ordinary gas, an increase in temperature causes the gas to expand, which cools it, which slows the nuclear reactions, a stabilizing feedback loop that allows ordinary stars to burn hydrogen for billions of years in steady equilibrium. But in a white dwarf, the pressure that holds the star up is quantum mechanical. It is set by density, not temperature. When carbon fusion begins and the temperature rises, the pressure does not change and the star does not expand. The heat has nowhere to go but further reaction. The fusion rate increases with temperature. Higher temperature means faster fusion. Faster fusion means more heat. More heat means faster fusion still. In the heart of the white dwarf, a runaway begins, a thermal runaway that accelerates without any counterbalancing mechanism, because the mechanism that would counterbalance it in any other kind of star simply does not exist here. The runaway begins as a subsonic flame, a deflagration, spreading outward from the ignition point near the white dwarf's center, propagating through the dense carbon-oxygen material, and leaving behind a wake of nuclear ash, silicon, sulfur, calcium, and ultimately nickel-56, the same iron peak nucleus produced by explosive nucleosynthesis in core collapse events. As the deflagration front moves, it stirs the white dwarf's interior, leaving large-scale chemical inhomogeneities and creating conditions that in at least some events may allow the deflagration to transition to a detonation, a supersonic burning front that races through the remaining unburned material faster than sound can travel through it. Whether the burning proceeds as a pure deflagration, a pure detonation, or some combination of the two, a question not yet fully resolved, the outcome is the same. The thermonuclear burning releases enough energy to completely unbind the white dwarf. There is no compact remnant. There is no neutron star left behind. There is no black hole. In under a second, the entire mass of the white dwarf carbon and oxygen that have been sitting inert for billions of years is converted into silicon, sulfur, calcium, and predominantly nickel-56. And this nuclear ash is flung outward at tens of thousands of kilometers per second in an expanding sphere of radioactive ejecta. A Type 1a supernova leaves nothing at its center. The star that was there, the dense crystalline remnant that had persisted perhaps for billions of years since its original death, is simply gone. What remains is an expanding shell of material glowing like a core collapse event on the energy of nickel-56, decaying to cobalt-56, and then to stable iron-56. The peak luminosity of a Type 1a supernova is extraordinary. At maximum brightness, such an event radiates roughly 5 billion times the light output of the Sun, a single exploding white dwarf, temporarily as bright as an entire galaxy of 100 billion stars. That brightness, extreme as it is, varies somewhat from event to event. Some Type 1a supernovae reach higher peak luminosities than others. For decades, this variation seemed to limit how useful such events could be as tools for measuring distance. If two events have different intrinsic brightness, comparing their apparent brightness tells you nothing reliable about how far away they are. Then a pattern was found. The intrinsically brighter Type 1 supernovae decline from peak brightness more slowly than the dimmer ones. The width of the light curve, The shape of the brightening and fading over days and weeks is correlated with the peak luminosity. A wider, slower declining light curve means a brighter event. A faster declining light curve means a dimmer one. This correlation is tight enough and stable enough that measuring the light curve of a Type 1a supernova at any distance gives enough information to calculate its intrinsic luminosity, and from that, its distance, by comparing how bright it intrinsically is to how bright it appears in the sky. A Type 1a supernova with a known intrinsic luminosity becomes a standard candle, a light source of known brightness that can be seen across billions of light years and used to measure the geometry of the universe. Astronomers searching for Type 1a supernovae in distant galaxies in the 1990s were using this method to measure the rate at which the expansion of the universe was decelerating. The expectation was that gravity, acting on the mass of the universe, would be slowing the expansion that began with the Big Bang. The distant supernovae should have been slightly brighter than they would be in a universe expanding at a constant rate, because if the expansion were slowing, the universe was smaller in the past, and the light had less distance to cross. The distant supernovae were slightly fainter than expected. Not brighter, fainter. They were further away than a decelerating universe predicted. The expansion of the universe was not slowing, it was speeding up. This finding, that the universe's expansion is accelerating, driven by some form of energy whose nature remains unclear, came from the light curves of exploding white dwarfs, measured with care across billions of light years. The supernovae themselves had no knowledge of this. They were simply carbon-oxygen white dwarfs, reaching a threshold and burning completely, their ejecta glowing on radioactive cobalt, their light curves following a pattern fixed by the physics of degenerate matter and thermonuclear burning. The meaning of the measurement was a human construction, but the signal was real, written in the slowly fading light of stars that had already been dead for billions of years before the observations began. In the months after a Type 1a supernova fades from peak brightness, the light curve settles into the slow exponential decline of cobalt-56 decay. The ejecta expand, their surface area growing, their temperature dropping. The spectrum evolves from the broad blended lines of iron group elements at high velocity near maximum light to narrower features as the ejecta thin and the photosphere retreats inward. Eventually, the ejecta become fully transparent, and the gamma rays from cobalt decay pass through them without heating anything, and the supernova fades below detection. What remains dispersed into the interstellar medium over thousands of years is the chemical output of the explosion. Iron peak elements dominate, primarily iron 56, the stable endpoint of the nickel 56 decay chain, but also chromium, manganese, cobalt, and nickel in proportions that carry the signature of the specific nuclear conditions during burning. Silicon, sulfur, calcium, and argon are present in the outer layers of the ejecta, produced during the earlier stages of the burning before the detonation consumed the innermost material. The oxygen and carbon that originally made up the white dwarf are largely absent from the ejecta. They were the fuel, and the burning was nearly complete. This chemical output is different in important ways from what a core collapse supernova produces. Core collapse events enrich the interstellar medium, primarily in elements lighter than iron, oxygen, neon, magnesium, silicon, with relatively modest iron output, since the iron-rich innermost core tends to collapse into the neutron star and stay there. Type 1a events produce very little of the lighter elements and contribute enormous quantities of iron. The interstellar medium around us and the chemical composition of the sun and the planets that formed from a molecular cloud already enriched by billions of years of stellar evolution, reflects the combined contributions of both types of explosions across cosmic time. The oxygen in the air comes mostly from core collapse supernovae, from the oxygen shells that were heated by the shock wave and driven into the interstellar medium over billions of years. The iron in the blood comes partly from core collapse events and partly from type 1a explosions, whose contributions accumulated more slowly, delayed by the long and spiral times of binary systems and the slow growth of white dwarfs to the Chandrasekhar limit, but which eventually contributed the majority of the galaxy's iron budget across cosmic time. Both paths, the massive star collapsing under its own weight, and the white dwarf quietly accumulating mass until its fuel ignites in a second, end in the same fundamental act. A star that has held itself together across vast timescales reaches a threshold it cannot cross by any means other than catastrophic restructuring, and in the crossing, it flings its chemical inventory into the surrounding medium. The gas that drifts outward from those explosions is not inert. It is enriched, it is seeded, it carries within it the nuclear products of processes that took millions or billions of years to arrange, compressed into seconds of violent release. The expanding shells of supernova eject a thin and cool across thousands of years. They sweep up surrounding interstellar gas, mixing their enriched material with the older, less processed material of the galaxy. The mixed gas accumulates in molecular clouds. The molecular clouds cool and contract under their own gravity, and the contraction is not smooth. It is fragmented, collapsing in many places at once, forming clusters of new stars. Those new stars begin their lives already carrying a chemical richness that no star formed earlier in the galaxy's history possessed. They are made of recycled material. Their planets are made of recycled material. And the slow, steady enrichment continues as massive stars in those clusters age and die and add their chemical output to the medium, as white dwarfs in binary systems accumulate mass across billions of years and eventually reach their limit and burn. In the time it takes a listener to fall asleep, perhaps 10 massive stars across the observable universe will reach the end of their silicon burning phase and begin to collapse. In the same interval, a Type 1a supernova somewhere in the observable universe will reach peak brightness, its cobalt-56 converting steadily to iron, its light crossing hundreds of millions of light years of space to reach a telescope somewhere, if one happens to be pointed in the right direction. The universe does not pause. The cycle of stellar death and chemical enrichment has been running for more than 13 billion years, and the rate at which it proceeds has not dropped to zero. It is slower now than it was when the universe was young and the rate of star formation was high. But it continues. The ejecta from supernovae that exploded before the sun existed are part of the gas and dust from which the sun and earth condensed more than 4.5 billion years ago. The ejecta from supernovae that have exploded since the sun formed are dispersed into the interstellar medium now, slowly mixing, waiting to be incorporated into molecular clouds, and eventually into new stars and planets. The process is not directed. There is no accumulation point, no final state being worked toward. There is only the physics of massive stars living briefly and dying violently, of compact remnants in binary systems accreting slowly toward a threshold, of radioactive isotopes decaying on timescales set by the nuclear force and contributing their energy and their daughter products to the surrounding medium. Months after a supernova explosion, the ejecta are still faintly luminous. The cobalt-56 that remains undecayed is still releasing gamma rays, and those gamma rays still find enough material to thermalize against, and the photons that emerge from the surface of the expanding cloud are still just visible to a sensitive instrument. The shell of gas is billions of kilometers wide now, still moving outward at thousands of kilometers per second, but thinning as its volume grows. The temperature at its surface is dropping. The spectrum is shifting toward the red. The light is fading. It will not go completely dark for a long time. Even when the optical emission falls below detection, the ejecta continue expanding into space, carrying within them the full chemical record of the explosion, the oxygen and silicon and calcium from the outer shells, the iron from the radioactive cascade at the center, the trace quantities of every element produced at every burning stage, and every explosive process the shock drove through the star. The atoms do not announce themselves. They drift, they disperse. They join the slow, cold chemistry of the interstellar medium, and in that joining, they become, eventually, indistinguishable from the surrounding material, incorporated into its composition, available to the next generation of stars and planets and whatever forms within them. The glow fades. The cloud expands into the dark. The iron drifts outward, cold and stable, waiting. A white dwarf the size of Earth sits in the dark between two stars, and it has been sitting there for a very long time. It does not burn. Nothing on its surface moves. Its interior is a lattice, carbon and oxygen nuclei, arranged in a crystal structure, so dense that a single teaspoon of it would weigh as much as a small car, compressed there not by temperature, but by a quantum pressure that requires no heat to sustain itself, only the obstinate refusal of electrons to share the same space. The dwarf is not warm the way a living star is warm. It carries the residual heat of a life it has already finished, cooling slowly, a few degrees every million years, as patient and still as a stone at the bottom of a cold river. The companion star beside it is another matter. That star is alive in the way all stars are alive, swollen, churning, its outer layers perpetually rising and falling in convective columns, its surface lit from within by processes running in its core. It is close enough to the dwarf that the space between them has a shape, a gravitational geometry with a narrow point, a saddle in space where the pull of one star equals the pull of the other. Material from the companion's outer atmosphere drifts toward that saddle and crosses it, a thin stream of hydrogen and helium flowing in a slow arc through the void between the two bodies. It settles onto the white dwarf's surface, atom by atom, over millions of years, and the white dwarf accumulates that mass in perfect silence. The stream is so thin it would be invisible from any distance. From a planet circling either of these stars, there would be nothing to see. Two stars in a close orbit, unremarkable among the hundreds of billions in the galaxy. One slightly smaller, slightly fainter. And between them, in the dark, a thread of gas falling slowly in one direction, adding mass so gradually that the change in any single year is far too small to measure. But the accumulation is real, and the dwarf is being filled. Carbon and oxygen crystals deepen inside it. The outer layers of hydrogen that arrive with each new parcel of accreted material undergo small thermonuclear flashes, brief surface events, not the end, just the star's surface, clearing away what does not belong, and the white dwarf beneath continues to grow. There is a rate at which this accretion must proceed for the dwarf to gain mass stably, a narrow band roughly 10 millionths of a solar mass per year, slow enough that the arriving hydrogen burns gently rather than all at once, fast enough that the dwarf does not simply shed the new material in recurring surface blasts. When the accretion holds that rate, the dwarf grows. It grows toward a number, The number is approximately 1.4 times the mass of the Sun. That number has a name, and the name belongs to a physicist who worked it out from first principles, calculating where the quantum pressure that holds a white dwarf together reaches its absolute limit. Subramanian Chandrasekhar, a young man on a ship crossing the Indian Ocean to England in 1930, worked through the equations in his cabin and arrived at a threshold above which no white dwarf, however old or however dense, could remain stable. The electrons that hold it up, packed so tight that quantum mechanics forbids any two of them from occupying the same energy state, cannot supply more pressure than a certain limit allows. Above that mass, something must give. Something always gives. The dwarf in its dark orbit has been approaching that limit for millions of years, and for most of that time, nothing about its approach would have been perceptible from outside. It brightens slightly as the accreted hydrogen burns on its surface. It dims when the flash is quiet, but the carbon-oxygen interior continues to grow. The crystalline lattice, already packed so tightly that ordinary physics would call it impossibly dense, grows heavier, and the electrons holding it up must work a little harder with each addition, and the margin between stability and collapse narrows, degree by invisible degree, across the long untroubled dark. There is another way this ending can begin. Across the galaxy, in other systems, there are not one white dwarf and one companion star, but two white dwarfs circling each other. They formed from two stars that lived and died at separate times, the more massive one finishing first, collapsing into a dwarf and waiting while its companion ran through its own long life, then collapsed in turn, leaving behind its own dwarf. Now both dwarfs orbit each other, cold and crystalline and dense, and the orbit between them is changing. It changes for the same reason that any close binary orbit changes. A moving mass curves space-time around itself as it travels, and a pair of masses orbiting each other continuously radiate that curvature outward in the form of gravitational waves, ripples spreading through space at the speed of light, carrying away small amounts of energy with each orbit. The energy lost is the energy of the orbit itself, and as the orbit loses energy, it tightens. Two white dwarfs circling each other at a separation of several solar radii may spiral slowly inward for hundreds of millions of years before the shrinking orbit carries them close enough to merge. That merger, when it comes, may carry a combined mass above the Chandrasekhar limit. The less massive of the two dwarfs, as it is pulled into the other, does not arrive gently. Tidal forces begin to stretch and distort it before the two surfaces touch. Material from its outer regions peels away and wraps around its more massive companion in a thick, rapidly rotating disk, heated by compression and stirred by the intense gravitational gradient. Whether the merged body ignites immediately or after a brief delay is not yet fully settled. The conditions at ignition differ from those of the steady accretion scenario, and the ashes those two paths leave behind may differ in small but measurable ways. The record of those differences is written in the light that comes after, and in the abundances of the elements produced. What both paths share is the fire. Inside a white dwarf, near the Chandrasekhar limit, carbon fusion does not begin gently. An ordinary star, when it begins fusing a new fuel, responds to the heat that fuel releases by expanding. The expansion cools the material, and the fusion rate drops, and the star finds a new balance. This self-regulation is the ordinary behavior of gas under gravity, and it is what keeps stars alive for millions and billions of years without burning themselves out all at once. A white dwarf is not gas under gravity. It is electrons under quantum law. The pressure holding a white dwarf up does not respond to temperature. It is set entirely by density, by how many electrons are packed into a given volume, and it does not increase when the temperature rises. This means that when carbon ignition begins somewhere inside the dwarf's interior and the temperature rises, the pressure does not rise with it, and the dwarf does not expand, and the fusion does not slow. Instead, the rising temperature accelerates the fusion rate, which raises the temperature further, which accelerates the fusion further, in a loop that has no natural break. The white dwarf's interior is a thermonuclear runaway waiting to happen, and the approach to the Chandrasekhar limit is the match. The ignition point is probably somewhere near the center, where the density is highest and the first deviations from stability occur. A kernel of carbon fusion begins in a region perhaps a few kilometers across, and the temperature at that kernel climbs within milliseconds to 1 billion Kelvin, and the burning front moves outward, converting carbon and oxygen into heavier nuclei as it expands. What happens next involves a sequence of events still studied in detail by researchers using the largest simulations available. The burning front begins as a deflagration, a subsonic flame moving more slowly than the speed of sound in the surrounding material, pushed by heat diffusion and hydrodynamic instabilities that wrinkle and fold the burning surface into a turbulent interface that grows faster than any smooth flame could. Whether this deflagration transitions to a detonation, a supersonic burning wave driven by its own shock, is one of the genuinely open questions in the physics of these events. The best current picture suggests that for at least some white dwarfs, in at least some ignition scenarios, the deflagration accelerates until detonation begins, either at the original burning front or in pockets of compressed, unburned fuel ahead of it. The distinction matters for what comes out the other side. What is certain is that the outcome is total. The entire white dwarf, every atom of carbon and oxygen in its crystalline interior, is consumed within roughly 1 second. The burning passes through neon and silicon and oxygen in an accelerating cascade, climbing the nuclear binding energy curve toward iron group nuclei. And in that single second, the white dwarf is converted almost entirely to nickel-56, to cobalt and titanium and calcium and silicon in proportions set by the temperature and density of each zone at the moment it burned. Between roughly 6/10 and 8/10 of a solar mass of the white dwarf typically ends up as nickel-56 alone, a radioactive isotope that carries within it the energy that will light the sky for months. The white dwarf that existed a second ago no longer exists. No neutron star remains. No black hole, no core of any kind. The energy released by the thermonuclear burning exceeds the gravitational binding energy of the white dwarf, and the entire body is unbound, not compressed, not shattered into large pieces, but vaporized into an expanding shell of nuclear ash moving outward at tens of thousands of kilometers per second. In the space where the white dwarf was, there is now only this shell, its edges invisible, its interior radioactive, its surface growing every second as it expands into the surrounding dark. Within the first few days, the ejecta are too dense for light to escape. The nickel-56 embedded in the shell decays to cobalt-56, with a half-life of just over 6 days, releasing gamma-ray energy that thermalizes in the surrounding material, absorbed, re-emitted, absorbed again, slowly working its way outward through the opaque expanding gas. As the ejecta thin, the light begins to leak out. The supernova brightens over roughly 2 weeks, climbing to a peak so intense it strains the imagination to hold. At maximum brightness, A Type 1a supernova radiates about 5 billion times the luminosity of the Sun from what was an hour before an object invisible to the naked eye at the distances where most of them occur. A single exploding white dwarf, smaller than Earth, temporarily shines as brightly as every star in its host galaxy combined, hundreds of billions of stars, and does so for days on end, visible to telescopes across billions of light years of space. Then the Cobalt 56 takes over the story. The nickel 56 produced in the explosion decays quickly, mostly in the first 3 weeks, but nickel 56 becomes cobalt 56, and cobalt 56 decays more slowly, with a half-life of just over 77 days. That longer-lived radioactive cobalt, embedded throughout the expanding cloud, continues releasing energy at a steady declining rate, and that energy continues to heat the ejecta and sustain their optical glow long after the original burst of nickel has dimmed. The brightness curve of a Type 1a supernova, from peak through decline, follows the decay clock of cobalt 56 with a precision that was recognized decades ago and has been used ever since to identify these events in distant galaxies. The curve has a shape, and the shape carries information, and that information turned out to hold one of the largest discoveries in the history of cosmology. Mark Phillips, working with data on Type 1a supernovae in the early 1990s, noticed that among these events there was a systematic relationship between how bright a supernova was at its peak and how quickly it faded afterward. The brighter ones declined more slowly, the dimmer ones faded faster. The two quantities moved together in a way that could be calibrated. If you measured how fast a Type 1a supernova declined from its peak brightness, you could infer how intrinsically luminous it was at that peak, regardless of how far away it was. And if you knew how intrinsically luminous it was, you could compare that to how bright it appeared and calculate the distance. This relation, the Phillips relation, transformed Type 1a supernova into what astronomers call standard candles, objects of known intrinsic brightness, whose distances can be read from their apparent dimness, the way a familiar light bulb can tell you how far away it is by how faint it looks. Ordinary stars cannot be used this way. They come in too many sizes and temperatures and luminosities, and without knowing a star's intrinsic brightness in advance, there is no way to calculate its distance from its apparent brightness alone. But a Type 1a supernova, standardized through the Phillips relation, functions as a calibrated beacon at a distance where almost nothing else is bright enough to see. In the 1990s, two teams of astronomers set out to use these beacons to measure the deceleration of the expanding universe. What they expected to find, from theory and common sense, was that the mutual gravity of all the matter in the universe was gradually slowing the expansion that began at the origin of space and time. The question was only how much. They found something else. The distant Type 1a supernova at distances of billions of light years were slightly fainter than the expansion rate of the nearby universe predicted they should be. Not dramatically fainter, not a difference obvious by eye or easy to dismiss as a calibration error. A small systematic dimness, carefully measured, carefully checked, surviving every test either team applied to it. A supernova dimmer than expected is farther away than expected. A supernova farther away than expected means the universe expanded more than expected in the time the light was traveling. And if the universe expanded more than expected, it must be expanding faster than it was before, not slowing under its own gravity, as everything had assumed, but accelerating, driven apart by something that acts like an energy distributed uniformly through space, pressing outward against the pull of gravity, growing stronger as the space it fills grows larger. That something was given the name dark energy, and what it is remains genuinely unknown. It fills the current best model of the universe. It constitutes the majority of the universe's total energy content, and the measurement that revealed it was made by comparing the brightness of distant exploding white dwarfs to the brightness of nearby ones, using a relationship between peak luminosity and decline rate, worked out from observations of a few dozen events in the years just before the discovery. The death of a white dwarf, which began as a slow accumulation of hydrogen atoms flowing across the dark between two stars, ended by rewriting the largest known structure of the universe, not through intention, not through any quality except the extraordinary regularity of what happens when a body of fixed composition exceeds a fixed mass limit and burns completely in a single second. The explosion was the same each time, governed by the same physics, producing the same amount of light by the same decay clock. That consistency, stretched across billions of light years and carefully measured by patient observers, comparing faint smudges of light on photographic plates and digital sensors, was what did the work. The instruments used were modest by the standards of late 20th century astronomy. The observations required years of accumulated data and the development of calibration techniques that did not exist when the project began. The researchers checking the results kept finding the same answer, even when they went looking for the error that would explain it away. No error appeared. The result was published in 1998, and the universe it described was a larger and stranger place than the one that existed in the scientific picture the morning before. A white dwarf at the threshold, still sitting in the dark, has no knowledge of any of this. It is a crystalline body, dense and quiet, with a thin stream of hydrogen arriving on its surface, and a companion star glowing at a distance of a few solar radii. Everything it contains, the carbon and oxygen packed into its lattice, the electrons stacked in their quantum layers, the slow heat from a life already completed, has been accumulating since the star it came from finished its hydrogen burning, perhaps billions of years ago, and shed its outer layers into the surrounding space, leaving this dense remnant behind. Inside the lattice, the carbon nuclei sit in their ordered positions, each separated from its neighbors by distances small compared to the radius of an atom, each one a nucleus of 6 protons and 6 neutrons, each one a piece of the universe's thermal and nuclear history. The carbon in a white dwarf was fused from helium in the core of the star before it became a white dwarf, in the same triple alpha reaction by which 3 helium nuclei combine at temperatures of roughly 100 million Kelvin to produce a single carbon nucleus. Every carbon nucleus in the white dwarf interior carries that origin, and the oxygen nuclei beside it carry a slightly later one, formed when an additional helium nucleus fused onto a carbon nucleus in the same hot core. When the white dwarf finally ignites, those nuclei will be rearranged completely. The carbon and oxygen that took hundreds of millions of years to accumulate will be consumed in a single second, transformed into iron group elements and intermediate mass nuclei that will expand outward through the host galaxy's interstellar medium over the tens of thousands of years it takes the ejecta to slow and mix with the surrounding gas. The iron those ejecta carry will one day become part of a molecular cloud, and part of a planet forming from that cloud, and part of the core of some future world where iron is abundant and useful and taken entirely for granted. The oxygen in those ejecta will mix into the same cloud and contribute to the raw material from which future solar systems assemble, and some portion of it may one day end up in the oceans of a world where the chemistry of water is the basis of everything that lives there. And none of that water will carry any record of where its oxygen was made or what kind of explosion freed it. For now, though, The white dwarf sits in the dark, and the stream of hydrogen continues to fall. The companion star does not know it is feeding a catastrophe. The stream of gas it loses to the saddle point between the two bodies costs it almost nothing in stellar terms, a tiny fraction of its total mass lost over millions of years, far less than what it loses to its own stellar wind, unnoticed in the overall account of its own long life. The companion star will still be there after the explosion. It will receive the ejecta as a blast, scorched and accelerated, and set ringing in oscillations that will take years to settle, but it will survive. Long after the light of the explosion has faded from the surrounding galaxy, the companion star will continue its ordinary business, fusing hydrogen in its core, warming whatever orbits it, and carrying in its photosphere the chemical history of everything that was in the cloud of gas and dust from which it formed. The white dwarf carries a different history. Its interior is a record of the star it came from, stripped of its outer layers and compressed to a remnant, and that record is about to be erased completely. Not lost exactly, transformed, distributed, sent across the galaxy in the form of new atoms that will themselves become part of future records, future stars, future worlds. The information is not destroyed. It is dispersed, and in that dispersal, it becomes available to everything that comes after. What comes after is a shell of expanding ash and a sky, somewhere in a distant galaxy, briefly lit by a white star no catalog had ever contained before. The light from that sky travels outward through the host galaxy's interstellar medium, through the intergalactic void, across distances so large that the universe itself will have expanded measurably in the time the light takes to arrive. A telescope, billions of years later and billions of light years away, will record that light as a faint smudge in a distant galaxy, brightening over 2 weeks, declining over months. Its decline curve following the decay clock of cobalt 56 with a precision that tells the observer exactly how bright it was when it peaked. The observer compares that brightness to the expected brightness of a standardized event at the measured redshift. The light is a little dimmer than it should be. Not by much, not obviously, not dramatically, not in a way that leaps out of the data. But when the numbers are gathered and the calibration is applied and the systematic errors are accounted for, the dimness persists, quiet and consistent, across event after event. The universe is expanding faster than it was before. That finding, that the space between galaxies is not gradually slowing under its own weight, but accelerating outward under the pressure of something invisible, reshapes the entire picture of what the cosmos is, where it came from, and where it is going. It is a picture drawn in the light of dead white dwarfs, their explosions standardized by a clock of radioactive cobalt, their distances calculated from a relationship between brightness and decline that was noticed by a careful observer working through a handful of nearby events. The white dwarf that is still accumulating hydrogen in its orbit has no awareness of any of it. The stream flows, the mass grows. The crystalline interior sits in its ordered silence, the electrons holding the nuclei apart with a pressure that requires no heat, only density, only the quantum insistence that no two of them may share the same state. The carbon and oxygen nuclei wait in their lattice positions as they have for millions of years. The distance to the Chandrasekhar limit, measured in the slow language of accreted solar masses, diminishes with each orbit of the companion star, each lap of the hydrogen stream, each quiet year in the long dark between these two bodies. The threshold is not a wall and not a cliff. It is a condition, and the condition is being approached as steadily and as inevitably as any physical process governed by fixed rules and patient time. The dark around the two stars is very still. The thread of hydrogen falls in a slow arc across the void. The white dwarf waits, crystalline and cold, accumulating the mass that will one day unmake it entirely and scatter it across the arms of the galaxy from which it came, and from which the universe's strangest story, written in the fading light of its own destruction, will eventually be read. Something about the stillness of that lattice, the ordered nuclei, the packed electrons, the patient accumulation across millions of years, has the quality of a breath held before a word. The carbon has been waiting since the red giant shed it. The electrons have been holding since the collapse. And the stream, thin as it is, falls without pause, adding its small weight to a calculation that the universe will finish in its own time, at a threshold where the rules that have held so long will simply, quietly, and completely fail to hold any longer. The companion star glows, the stream flows, the white dwarf receives it all, one slow atom at a time, and the space between them is dark and without sound. Deep inside a star in its final hours, where the temperature runs hotter than 10 billion degrees, the matter is arranged in layers, the way ancient stone is arranged in canyon walls, each stratum a record of a different era, pressed inward by everything that came after it. The outermost layer is hydrogen, cool and vast. Below it, helium, then carbon, then neon, then oxygen, then silicon. And at the very center, denser than anything the surface knows, sits an iron core no wider than a small planet, silent and held. That layered structure is not an accident. It is a history. Each shell marks a burning stage that ran its course and left its products behind. Hydrogen burning for millions of years, helium burning for hundreds of thousands, and then shorter and shorter intervals as the star burned heavier and heavier fuels, compressing the record of each era into a thinner and thinner ring. Silicon burning, the last stage, lasted only days. The star worked its way inward through its own past, and what it left behind was this: concentric zones of different elements, stacked like the rings of a tree, that measured not years, but epochs of nuclear fire. The iron at the center is the end of that sequence, not because the star ran out of material, but because iron sits at the peak of the binding energy curve, the point at which fusing iron together would consume energy rather than release it. The star reached the one element it could not burn, and in that stillness, with the iron core held up by nothing more than the quantum resistance of packed electrons, the entire architecture of the star's life became the architecture of what was about to scatter across space. The supernova shock that tears through those shells in the seconds after collapse does something the slow hydrostatic burning never did. It heats each layer as it passes through, and the heat is extreme enough to restart nuclear reactions at speeds the star's quiet interior never approached. When the shock reaches the oxygen-burning shell, it raises the temperature to 5 billion degrees for a fraction of a second. Not long enough to be called a burning stage, but long enough to produce new elements in proportions different from those the shell had produced on its own. Silicon forms, sulfur forms, calcium forms. The shock is not only a force of destruction, it is a second wave of nucleosynthesis, brief and violent, and leaving its own chemical signature in the expanding gas. This distinction matters. The star built one set of elements through months and years and millennia of slow burning at equilibrium. The explosion built a second set through an instant of extreme heat that lasted less than the time between one heartbeat and the next. Both sets of elements are real. Both travel outward together in the ejecta, but they carry different fingerprints, and those fingerprints can still be read, billions of years later, in stars that formed from the scattered remnants of that explosion. The oxygen shell is the first to be reached by the shock, and it is one of the thickest shells in the star's structure. The elements produced there during the star's long hydrostatic oxygen burning stage, sulfur, argon, calcium, and iron group nuclei, are already present. The shock adds to them and shifts the proportions and sends all of it outward at thousands of kilometers per second. The calcium in bone and tooth and shell, the calcium that builds the structures that hold the bodies of complex animals together, was produced in this kind of event, in the oxygen-burning shells of massive stars, both during their slow lives and in the violence of their deaths. Below the oxygen shell, closer to the core, the silicon shell had already converted itself almost entirely to iron group elements before the collapse began. At the center sits the iron core itself, dense and inert. But just outside the core, in the region where the shock's energy is highest, something new forms, nickel 56. Not stable nickel, not the kind that persists. Nickel 56 is radioactive, and it is produced in enormous quantities, often more than half a solar mass of it, in the innermost ejecta of a core collapse supernova. It is unstable, and its instability is the reason the explosion stays luminous for weeks after the star has died. Nickel 56 decays into cobalt 56 in about 6 days. The half-life is short enough that the decay begins almost immediately, releasing gamma-ray photons from within the expanding ejecta. Cobalt 56 is also radioactive, with a longer half-life of about 77 days. It decays into stable iron 56, releasing more gamma rays. Those gamma rays scatter through the gas, thermalizing, converting from high-energy photons into the lower-energy light that can escape through the ejecta and reach an observer. Weeks after the initial explosion, when the blast energy has faded, it is this decay chain that keeps the remnant glowing. The light from a supernova, in the weeks and months after peak brightness, is in a very direct sense the light of iron being born. A satellite called the Solar Maximum Mission was watching the sky in February of 1987 when a star in the Large Magellanic Cloud, a small companion galaxy visible from the southern hemisphere, exploded. The supernova was bright enough to see without a telescope, and within the weeks that followed, the satellite detected something that had been predicted but never before observed: gamma-ray photons at specific energies emerging from the direction of the supernova with energies of 847 million electron volts. That precise energy is the fingerprint of cobalt 56 decay. The detection confirmed directly that supernovae produce iron through this radioactive pathway, not by fusing iron directly, not by any other process, but through the decay of nickel 56 into cobalt 56 into iron 56, one step at a time, the gamma rays escaping through the expanding gas and arriving at the satellite's detectors from 160,000 light-years away. The cobalt 56 gamma ray line from that event was not a vague signal. It was a precise spectral feature, a single energy, clean and identifiable. It is the kind of measurement that leaves no room for alternative interpretation. The iron in the ejecta of a core collapse supernova comes from radioactive decay. The light that makes the supernova visible for months comes from the same process. The explosion is, in a real and physical sense, powered by the slow conversion of one element into another, nickel becoming cobalt becoming iron, each step releasing energy that keeps the remnant warm enough to be seen. The iron 56 that forms at the end of this chain is the most stable nucleus that ordinary matter produces in core collapse supernovae. It is stable in the precise sense that it sits at the very bottom of the nuclear binding energy curve, bound more tightly per nucleon than any other common nucleus. The core of the dying star was held up by iron that could not burn. The ejecta of the dying star produce iron through the decay of nickel. Iron frames the beginning of the collapse and the end of the explosion both. There is a kind of geometry to this, the elements arranged not only in the layers of the dying star, but in the time it takes for each layer's contribution to arrive at a distant observer. The outermost layers, moving fastest, carry the products of the earliest burning stages, hydrogen, helium, and the carbon and oxygen from helium burning. The middle layers carry neon, magnesium, oxygen. The innermost layers carry silicon, sulfur, calcium, and the radioactive nickel that will slowly become iron. A supernova is not just an explosion. It is a sequential delivery of nucleosynthetic history unrolled over days and weeks as different layers of the ejecta expand and cool and become transparent. Carbon and oxygen were the first of the heavier elements the star built. They formed in the helium-burning core when 3 helium nuclei fused together to form carbon-12 in a reaction so sensitive to the precise energy levels of the carbon nucleus that had the nuclear physics been slightly different, carbon would not exist in abundance at all. That sensitivity is not a design. It is a coincidence of nuclear structure. The energy level of the carbon nucleus is almost exactly matched to the energy of 3 helium nuclei coming together, and the match makes the reaction fast enough to proceed. Carbon formed in enormous quantities in helium-burning cores, and when helium burning continued past carbon, some of those carbon nuclei captured an additional helium nucleus and became oxygen-16. The ratio of carbon to oxygen in the ejecta of massive stars depends on the precise rate of that second reaction, a rate still measured to higher and higher precision by nuclear physicists. Carbon and oxygen, scattered by supernovae and accumulated in the interstellar medium over billions of years, became the raw material for everything that followed. Carbon is the backbone of organic chemistry. Oxygen is the most abundant element in the Earth's crust and the second most abundant in the human body. Both were made in helium-burning cores, in stars that had already spent millions of years on hydrogen and then burned helium for hundreds of thousands more, and both were released into space when those stars ended. The carbon and oxygen in the world come from the middle chapters of stellar lives, delivered by the violence of stellar deaths. Neon and magnesium are the products of carbon burning, which begins after the helium shell has receded and the core temperature has risen to about 500 million degrees. In carbon burning, 2 carbon-12 nuclei fuse together, producing neon-20 and magnesium-24 in roughly equal proportions, along with alpha particles and protons that participate in further reactions. The carbon-burning shell in a pre-collapsed star sits between the helium shell and the oxygen shell, and it is from this layer that the neon and magnesium in the universe largely come. These elements are less abundant than carbon and oxygen, but they are not rare. Magnesium is the 8th most abundant element in the Earth's crust. It is in the minerals and rock, in the green of chlorophyll, in the chemistry of every living cell that uses magnesium ions to manage the processes of energy metabolism. Oxygen burning follows carbon burning as the core contracts further and the temperature rises past 2 billion degrees. Oxygen-16 nuclei fuse together to produce primarily sulfur-32 and silicon-28, with smaller quantities of phosphorus and magnesium. Silicon is the second most abundant element in the Earth's crust. Sulfur is the 10th. Phosphorus, produced in smaller quantities in oxygen-burning shells and through other processes in supernovae, is essential to the chemistry of life. It forms the backbone of DNA, the currency of cellular energy, the structural element of cell membranes. Each of these elements traces its abundance back through the oxygen-burning shells of massive stars, built over centuries in hydrostatic burning and scattered in seconds by the explosion. Silicon burning is the last quiet stage before collapse, and it proceeds by a mechanism different from the earlier stages. Rather than two silicon nuclei fusing directly, the Coulomb barrier between them is too high. Silicon burning works by photodisintegration, where high-energy photons break some silicon nuclei into lighter fragments, and those fragments are captured by other nuclei in a sequence of reactions that moves the composition steadily toward the iron group. The result is a mix of iron, cobalt, and nickel in proportions close to nuclear statistical equilibrium, the distribution of nuclei that would exist if the reactions were fast enough to reach their thermodynamic minimum. At the temperatures of silicon burning, they very nearly are, and the product, iron 56 and its close neighbors, is what fills the core. The sulfur and calcium produced in oxygen and silicon burning are worth pausing over. Calcium, element 20, is the most abundant metal in the human body by mass. It is in teeth and bone and the signaling chemistry of nerves and muscles. The calcium that forms those structures came largely from the oxygen-burning shells of massive stars. Sulfur, element 16, is in every protein. It forms the chemical bridges that give proteins their three-dimensional shape. Its origin is the same chain of processes, massive stars burning oxygen in their cores, in shells over millions of years, then scattering those shells into the interstellar medium. This is one of the stranger recognitions that the science opens onto, that the elements in a living body are not uniformly ancient, not from the same moment or the same kind of event, but from a series of different nuclear fires in different kinds of stars at different times. The hydrogen in water is nearly as old as the universe itself, formed in the first few minutes after the Big Bang. The carbon and oxygen in organic molecules came from helium-burning cores of stars that lived and died billions of years before the sun formed. The neon and magnesium in proteins and minerals came from carbon-burning shells. The sulfur and calcium and silicon came from oxygen and silicon burning, and the iron in blood, hemoglobin, the iron in the Earth's core, the iron that gives red clay its color, came from the radioactive decay of nickel 56, scattered by supernova shockwaves, and gathered slowly into the solar nebula over billions of years. The body is not built from one kind of stellar debris. It is built from a layered history, elements produced at different depths, in different burning stages, in different generations of stars, assembled first in the interstellar medium, then in the solar nebula, then in the chemistry of early Earth, then in the slow processes of biology. To read the periodic table of elements in the body is to read a stratigraphy as real as the layers of rock in canyon walls. Each element points back to a specific temperature range, a specific nuclear process, a specific position in the interior of a massive star. The iron in blood is worth holding here for a moment. Iron 56 is the endpoint of the nickel 56 decay chain, which itself forms in the innermost ejecta of core collapse supernovae and in the thermonuclear explosions of white dwarfs. It is the most tightly bound nucleus that these processes produce in abundance. In hemoglobin, each molecule carries 4 iron atoms, each at the center of a heme group, and it is the iron that binds oxygen and carries it from the lungs to every cell in the body. The iron in hemoglobin was forged in the cores and ejecta of stars that died before the sun was born. It traveled through the interstellar medium in the form of dust grains and gas, was incorporated into the solar nebula, settled into the young Earth, cycled through geology and ocean chemistry, and eventually into biology. The iron atom in a red blood cell has a history stretching back billions of years, through at least one stellar death, and possibly more. The ratio of certain elements to each other in old stars carries this entire history as a kind of fossil record. Stars that formed early in the Milky Way's history, when only a few generations of massive stars had yet lived and died, show a distinct chemical signature. They have high ratios of oxygen to iron and high ratios of magnesium to iron, and elevated abundances of silicon and calcium relative to iron. These ratios are the signature of core collapse supernovae, which enrich the interstellar medium quickly, on timescales of millions of years, with the products of oxygen and silicon burning. Iron enrichment from a different kind of stellar death lags behind. It takes much longer to arrive. The element ratios in old stars are not evenly distributed. Some extremely old stars show very high abundances of oxygen and magnesium and almost no iron at all compared to the Sun. Others show moderate iron enrichment alongside the elevated alpha elements, and the trend across the whole population of old halo stars is clear. As the iron abundance increases from very low values towards solar, the ratio of oxygen to iron and magnesium to iron decreases. The curve describes a history: early enrichment by massive stars, fast, abundant in alpha elements, deficient in iron, later enrichment by a process that produces iron in much larger quantities. The chemical evolution of the galaxy is written in those ratios, readable in the spectra of stars still shining today. Oxygen, magnesium, silicon, sulfur, calcium, and titanium are called the alpha elements because each nucleus is built from an integer number of helium nuclei, which physicists call alpha particles. Carbon-12 is 3 helium nuclei, oxygen-16 is 4, neon-20 is 5, magnesium-24 is 6, silicon-28 is 7. These nuclei form in successive burning stages and are ejected by core collapse supernovae in large quantities. Their shared structure reflects their shared origin. They are the products of the alpha capture chain, the sequence of helium nucleus additions that builds the heavier elements in stellar interiors. Iron is different. Iron does not form by alpha capture in the same sequence. The iron produced in large quantities by one kind of stellar death is a late contributor to the interstellar medium. It arrives on a much longer timescale, hundreds of millions to billions of years after the first massive stars die. And when it arrives, it lowers the alpha to iron ratios of the gas that forms new stars. That is why younger stars, like the Sun, have solar ratios of these elements. The interstellar medium they formed from had already been enriched by that later iron source, evening out the ratios left by the earliest massive stellar deaths. The nature of that later iron source and the time scale on which it operates are readable in the chemical record of stellar populations, not directly observed in the explosions themselves, but inferred from the abundance patterns of thousands of stars measured over decades of spectroscopic surveys. The fossil record written in starlight is as detailed and as patient as the fossil record written in stone. Both require the same willingness to read slowly, to follow ratios and trends across large populations, and to trust that the patterns carry real history. A star that formed 12 billion years ago from gas enriched by only one or a handful of earlier supernovae carries the nucleosynthetic output of those specific events in its photosphere. The elements that star fused in its own interior are buried, not accessible without a spectrograph aimed at the outer layers. The photosphere, which is thin and well mixed and roughly unchanged since the star formed. When a spectrograph spreads that starlight into a spectrum, the absorption lines produced by each element in the photosphere reveal the composition of the gas cloud the star was born from. 12 billion years later, the photosphere still holds the ratio of oxygen to iron, of magnesium to iron, of europium to iron that the cloud had when the star formed. The star is a closed container for the chemical record of its formation environment. There are stars in the galactic halo, the old, loosely distributed population of stars that orbit the Milky Way at large distances from the disk, with iron abundances thousands of times lower than the Sun's, and yet with normal or elevated abundances of carbon and oxygen and magnesium. These stars formed before the galaxy had built up much iron at all, from gas that had been enriched by only the earliest generations of massive supernovae. They are the oldest chemical fossils in the Milky Way, and their spectra have been measured with enough precision to reconstruct the element yields of the supernovae that enriched their birth clouds. The shape of a core-collapse supernova's nucleosynthetic output, how much oxygen it produces, how much magnesium, how much silicon, in what proportions, can be tested against the abundances in these ancient halo stars, because the halo stars preserved those yields nearly unchanged. The matching is not always perfect. Some extremely iron-poor stars show peculiar enhancements of specific elements, very high carbon or very high strontium, or patterns that suggest they formed from the output of a single, unusual supernova, rather than a well-mixed average of many. These stars are called carbon-enhanced metal-poor stars, and they are a small but important population because they preserve the chemical fingerprint of individual ancient explosions rather than the statistical average of many. The supernova that enriched the birth cloud of such a star was, in some sense, unusual, or perhaps representative of a class of events that were common early in cosmic history and less common now. The interstellar medium is the reservoir through which all this nucleosynthetic output passes before becoming new stars. A supernova remnant expands for tens of thousands of years, sweeping up interstellar gas and mixing its ejecta into the surrounding medium. The outermost layers of the ejecta, hydrogen and helium, mix first, enriching the immediate surroundings only slightly. The inner layers, oxygen, silicon, the radioactive nickel, decaying to cobalt, decaying to iron, mix later as the remnant slows and its structure becomes turbulent. Eventually, over millions of years, the ejecta are dispersed into the general interstellar medium, their chemical identity dissolved into the broader composition of the galaxy's gas. A single core collapse supernova ejects between a few and several tens of solar masses of material, depending on the mass of the progenitor star and how much mass it lost to stellar winds during its life. A significant fraction of that mass, sometimes as much as half, is the helium envelope and the hydrogen envelope that the shock swept through on its way out. The chemically enriched inner ejecta, the oxygen, silicon, sulfur, calcium, and the nickel-56 that becomes iron, make up a smaller fraction by mass, but the more interesting fraction by chemistry. Each supernova injects this material into the interstellar medium, and the cumulative output of millions of supernovae over galactic history is what brings the Milky Way's interstellar medium to its current composition. Hundreds of millions of core collapse supernovae have occurred in the Milky Way since its stars first began to form. The current composition of the interstellar medium, its oxygen abundance, its carbon abundance, Its silicon and magnesium and sulfur reflects the accumulated output of all those events summed over billions of years and distributed across the galaxy's volume. The interstellar medium is, in this sense, a kind of average supernova ejecta, diluted by the primordial hydrogen and helium that has always been present, and modified by the timescales on which different types of stellar deaths contribute. The chemical gradient across the disk of the Milky Way, the fact that stars in the inner disk are more metal-rich than stars in the outer disk, reflects the higher rate of star formation and supernova activity in the inner galaxy, where the gas density was higher and massive stars have been forming and dying at higher rates for longer. The outer disk has been enriched more slowly, and its stars carry lower abundances of the elements that supernovae produce. This gradient is measurable from the spectra of stars at different distances from the galactic center, and it traces the uneven geography of stellar death across the galaxy's history. The stellar populations of different ages tell the same story in a different dimension. The oldest stars in the Milky Way formed when the galaxy was young and the interstellar medium was metal poor. The youngest stars formed from gas that had been enriched by billions of years of supernovae, and they carry solar or supersolar abundances of the heavy elements. Between those extremes, the abundance of every element in stellar photospheres increases with decreasing age, not smoothly or uniformly, because the history of star formation in supernovae was uneven, but in a trend that is real and consistent and well documented across hundreds of thousands of stellar spectra. The silicon in a computer chip, and the silicon in a grain of sand, and the silicon in the mineral structure of bone all trace back to the oxygen-burning shells of massive stars scattered across the Milky Way over its history. The sulfur in a protein, the calcium in a shell on a beach, the magnesium in the green of a leaf in summer. Each of these was assembled in a burning shell inside a star that no longer exists, ejected by the star's death, dispersed through the interstellar medium, gathered into a molecular cloud, incorporated into the solar nebula, settled into the young Earth, and eventually into the chemistry of the living world. The journey from stellar interior to the present moment is neither short nor simple. It involves multiple phases of dispersal and reaggregation, multiple chemical transformations, multiple geological and biological cycles. But the nuclear identity of each element, the number of protons in its nucleus, the binding energy that holds it together, the specific nuclear process that assembled it, was fixed in the moment it was forged. Carbon-12, made in a helium-burning core 3 billion years ago, is the same carbon-12 that forms the backbone of an organic molecule today. The nuclear event that created it left a mark that no subsequent chemistry can erase. There is something quietly grounding in that constancy, the idea that beneath all the transformations of matter, beneath all the cycling of elements through stars and gas and rock and water and biology, the nuclear identity of each atom is preserved unchanged. The oxygen atom has 16 protons in its nucleus because it was made by the fusion of 4 helium nuclei in a stellar core at a specific temperature billions of years ago. That fact is still true. Nothing that happened to the oxygen atom since, no chemical reaction, no geological cycle, no biological process, has changed the number of protons. The element is the same. The star that made the oxygen in the air, breathed by the animals of the Cambrian, the star that made the calcium in the bones of a dinosaur, the star that made the iron in the hemoglobin of every mammal that has ever lived. These are not the sun. They are older stars, stars that lived and burned and died before the sun was born, stars whose names, if they had names, are unrecoverable. The elements they made are recoverable, though, in the composition of the world, in the ratios of elements in ancient stars, in the chemical fingerprints of supernova ejecta measured by spectrographs aimed at distant galaxies. The stars are gone, the matter remains. In the spectrum of a very old star in the halo of the Milky Way, measured with enough precision to resolve the individual absorption lines of dozens of elements, there is a record of nucleosynthetic events that happened before the sun formed. The depths of those lines, the wavelengths at which they appear, the ratios of one element's signature to another, all of this is still there, preserved in the photosphere of a star that has been burning quietly for 12 billion years. The supernova that seeded that star's birth cloud may have happened 100 million years before the star formed. The star has been carrying the chemical record of that event ever since, through 12 billion years of slow hydrogen burning, unchanged in the layers that a spectrograph can read. That record is one of the quietest forms of memory in the universe. Not written in rock or ice or biological tissue, not stored in any structure that thinks or feels, but preserved in the physics of atomic transitions, in the wavelengths of light emitted and absorbed by electrons moving between energy levels. A photon leaves the photosphere of a halo star, travels for thousands of light years across the galaxy, enters a telescope, is spread into a spectrum by a diffraction grating, and arrives at a detector, and in the depth of one absorption line, at one specific wavelength, the ratio of magnesium to iron from a supernova that happened 12 billion years ago is still readable. The universe does not erase its records. It stores them in starlight and waits. The interstellar dust that drifts through the Milky Way in thin clouds, occasionally visible as dark patches against the glow of more distant stars, is partly the residue of supernova ejecta. Silicate grains, carbon grains, iron oxide grains, these form in the cooling ejecta of stellar explosions and in the winds of dying stars, and they are preserved in the interstellar medium for long periods before being destroyed by the ultraviolet light and shock waves of the next generation of stellar activity. When a molecular cloud collapses to form a new star system, the dust grains in the cloud carry with them the isotopic fingerprints of the stellar deaths that produced them, specific isotope ratios that differ from the average interstellar composition and point to a particular stellar source. Presolar grains, microscopic mineral inclusions found in primitive meteorites that fell to Earth, preserve these isotopic fingerprints in extraordinary detail. A presolar silicon carbide grain, a few micrometers across, can carry within its crystal structure isotopic ratios of carbon, nitrogen, silicon, and rare elements that match the expected output of a specific type of stellar event, a core collapse supernova, or an asymptotic giant branch star, or another kind of stellar death entirely. These grains formed in the ejecta of their parent star, drifted through the interstellar medium for millions of years, were incorporated into the solar nebula before the sun formed, and survived the 4.5 billion years of solar system history intact, waiting in the matrix of a primitive meteorite until a laboratory dissolved the meteorite's common material and isolated the exotic grains for measurement. The presolar grains are the closest thing that exists to actual samples of supernova ejecta. They are not spectra of distant events. They are physical objects, measurable grain by grain, with isotopic ratios that carry the nucleosynthetic fingerprint of the stellar process that made them, and many of them carry the isotopic signature of core collapse supernovae, elevated ratios of specific silicon and carbon and oxygen isotopes that match the predicted yields of massive stellar deaths and cannot be produced by any other process in the solar system's history. The silicon carbide in a presolar grain, the iron in hemoglobin, the calcium in bone, the oxygen in the air, The carbon in every organic molecule, in every living thing. These are not the same kind of material in the sense of sharing a single origin. They were made in different stars, in different burning stages, in different kinds of explosions, at different times, spread across billions of years. What they share is the path from stellar interior to interstellar medium to solar nebula to planetary body to chemistry. They share a history of transformation and dispersal, not a single source. The periodic table, read as a map of origins, shows that no single stellar event or process accounts for the full composition of the world. Hydrogen and helium are primordial from the first minutes of cosmic history. Lithium, beryllium, and boron are made by cosmic ray spallation in the interstellar medium, not in stars at all. Carbon and oxygen come from helium-burning cores. The neon, magnesium, silicon, sulfur, argon, and calcium are products of the successive burning stages of massive stars. The iron group elements, iron, cobalt, nickel, come from radioactive decay chains in supernovae ejecta and from the thermonuclear destruction of white dwarfs. And the elements heavier than iron, gold, platinum, uranium, and the rest require a different process entirely, one that operates in the densest and most extreme environments the universe produces. The boundary at iron is not arbitrary. It is set by nuclear physics, by the binding energy curve that reaches its peak at iron 56 and descends on both sides, making iron the most stable common nucleus and making the production of heavier elements require an input of energy rather than a release. Below iron, stellar burning releases energy. Above iron, building heavier nuclei requires a neutron flux so dense and an environment so extreme that ordinary stellar burning cannot provide it. The elements below iron were made in the long lives and violent deaths of massive stars, accumulating in the interstellar medium over billions of years of galactic history. What lies above iron has a different address. The old halo stars that carry the highest ratios of oxygen to iron and the lowest overall metal abundances are quiet tonight, most of them far from any dust cloud, far from any star-forming region, moving in slow orbits around the galactic center that have been largely undisturbed for billions of years. Their photospheres hold the chemical record of the earliest stellar deaths in the Milky Way. The light they emit, spread by a spectrograph into the lines of oxygen and magnesium and silicon and iron, is still carrying that record outward across space, as it has been for billions of years, available to anyone with a large enough mirror and the patience to measure carefully. The carbon in the leaves on trees right now, green and catching sunlight in 1,000 forests, was assembled in a helium-burning stellar core that no longer exists. The calcium in the chalk of old ocean sediment, built from the shells of small marine organisms that lived and died hundreds of millions of years ago, came from the oxygen-burning shells of stars that died before the sun formed. The iron in the deep magnetic field of the Earth, circulating in the liquid outer core, was scattered by supernova shock waves and gathered into the solar nebula 4.5 billion years ago. The elements in the world are not native to it. They arrived from older places, from the interiors of stars, from the violence of their deaths, from the long, slow dispersal of their matter through space. The burning is finished in those old stars. The shock waves have long since faded into the surrounding gas. The remnants, once bright with X-ray and optical emission, have merged with the interstellar medium, their edges no longer distinguishable from the background. What they left behind is not visible as a structure anymore. It is dissolved into the composition of everything, the gas in the next molecular cloud, the dust grains drifting through the galactic plane, the silicon and oxygen and iron in the rocky bodies of every solar system that formed from gas, those supernovae, enriched. The record persists, though, in the old stars still burning in the halo, in the presolar grains locked in primitive meteorites, in the isotope ratios of ancient rock, in the absorption lines of starlight crossing billions of years of space. The history of every element that makes up the solid world, and the living world, and the air and water and stone, that history is written in the composition of matter itself, element by element, isotope by isotope, all of it preserved in the physics of atomic nuclei, that nothing subsequent has altered. The stars that made the elements burned and were scattered long before there were eyes to watch them. The matter they made drifted through cold, dark space for longer than the Earth has existed, and then it gathered, slowly, into the molecular cloud that became the Sun and its planets, and into the chemistry that became, in time, the living world. The iron in an old red star burning quietly in the halo tonight, carrying within its spectrum the abundance ratios of ancient supernovae, is kin to the iron in every red blood cell in every warm body on Earth. The kinship is not poetic, it is nuclear. It is written in the number of protons, fixed at the moment of formation and unchanged across all the vast, unhurried time since. Two neutron stars circle each other in the dark between galaxies, each one smaller than a city and heavier than the sun. Their orbit is not stable. It has never been stable. Since the moment the second one formed, the distance between them has been shrinking, not quickly, not in any way that could be measured in a human lifetime, but by a few centimeters, with every revolution, as though the space between them is being drawn out through some invisible drain. That drain is space-time itself, carrying their orbital energy away as ripples too faint to feel, spreading outward at the speed of light through hundreds of millions of light years of emptiness. They have been spiraling like this for a very long time, tens of millions of years, perhaps hundreds of millions. Each one is the collapsed remnant of a star that burned and died long before the first animal developed eyes on Earth. Stars so massive that when they exhausted their fuel, they fell inward in under a second, their cores compressing past the density of iron, past the density of individual atoms, until the protons and electrons of their cores merged into neutrons and the collapse stopped. What remained was not quite matter in any familiar sense, a sphere of neutrons packed as densely as an atomic nucleus, 10 miles across, with a surface gravity so strong that light itself bends as it leaves. Two of these objects, each a few times heavier than the sun, circling each other in silence. The silence is total because there is no medium to carry sound, but there is something passing through the space between them, and through the space between galaxies, and through the spaces between all things everywhere. The gravitational waves they generate are not waves in any material. They are compressions and stretches in the geometry of space, a lengthening of distances in one direction, a shortening at right angles, propagating outward like rings on still water from a stone dropped in. The rings are extraordinarily faint by the time they spread to any significant distance. But near their source, near the two circling neutron stars, the emission is continuous and the effect is real. The orbit shrinks, the period shortens, the stars draw closer. As the separation falls, the orbital speed rises. Two city-sized masses, heavier than the sun each, moving faster and faster around each other, not over millions of years now, but over months, then weeks, then hours. The gravitational wave emission grows stronger as they speed up, which drains the orbit faster, which raises the speed further. In the final seconds, the two stars are moving at a significant fraction of the speed of light, separated by only a few miles, circling each other dozens of times per second. The gravitational waves are no longer faint. They are among the most powerful events in the observable universe. Ripples in space-time strong enough, if a detector were close enough, to stretch and compress matter by a detectable fraction of the width of a proton, than the surfaces touch. The less massive of the two stars does not survive contact as a coherent object. Tidal forces tear at it as the gap closes, the same kind of force that raises tides on Earth when the moon pulls its near side slightly more strongly than its far side, but here scaled up to the tidal field of a neutron star pulling on a neutron star. The crust of the smaller star stretches toward its companion, and then the star comes apart, its matter wrapping around the heavier core in a spiral of material so dense that an entire mountain range, compressed into a drop of it, would still be far lighter than what actually flows there. The merger occupies a time interval that cannot be tracked by any human sense, a millisecond, perhaps two. The entire event, from first contact to merged remnant, is over before a nerve signal could cross a fingertip. What remains is unclear, and that uncertainty is honest. The merged object may be a single more massive neutron star, held up briefly by its own spin. It may collapse almost immediately into a black hole. The details depend on the masses of the two original stars, and on the internal physics of neutron star matter, matter so compressed that the ordinary rules of atomic physics no longer describe it well, and whose behavior in the most extreme conditions is still not precisely known. What is known is what comes out. Gravitational waves from the final inspari and merger, a brief intense burst of gamma radiation, and a cloud of expanding matter launched outward from the collision at a significant fraction of the speed of light, carrying within it something the universe had been building toward for a very long time. On the 17th day of August, in the year 2017, two detectors in the United States and one in Europe felt a faint stretch and compress in space-time, a pattern in the data lasting roughly 100 seconds, rising in frequency and amplitude, the unmistakable signature of two masses spiraling together and merging. The detectors are extraordinarily sensitive instruments, long tunnels in an L shape, miles to a side, with laser light bouncing between mirrors and measuring the distance between them to a precision far smaller than the nucleus of an atom. The signal that arrived was tiny, but it was there, and its shape matched what general relativity predicts for the final inspiral of two neutron stars, and within seconds the data was being read by physicists in the middle of their working day. 1.7 seconds after the gravitational wave signal ended, a space telescope built to detect gamma rays registered a brief pulse of the highest energy light in the known universe. The pulse lasted only 2 seconds. The source was in a galaxy roughly 130 million light-years away, a galaxy in the constellation Hydra called NGC 4993. In the following hours, optical telescopes around the world and in orbit turned toward that galaxy, and within 11 hours they had found it, a new point of light, appearing in the outskirts of the galaxy where nothing had been visible before. It was blue at first. Then it faded from blue and brightened in the red and infrared. After a few weeks it was gone. That transient object, that temporary glow, had a name already waiting for it in the theoretical literature, coined in anticipation of the day it would be observed. A kilonova. Not a supernova. Something different. Fainter than a typical supernova, but not faint. At its peak, the kilonova from GW 1708 1.7 radiated roughly 1,000 times the light of an ordinary nova. The color change from blue to red was significant. It was a clue embedded in the light itself, pointing toward what the ejecta contained. The blue light came first because the outer, fastest layers of the ejected material were relatively low in a particular class of heavy elements, lanthanides, the dense, rare elements that sit below the main body of the periodic table, elements with electron shells so complex and so full of closely spaced energy levels that they absorb and re-emit light with extreme efficiency across a wide range of wavelengths. Material rich in lanthanides is opaque to visible light in a very specific way. It forces photons to scatter and rescatter, converting their energy toward the red and infrared before they escape. Where the early blue emission came from material with fewer of these heavy atoms, the later red emission came from a deeper, slower layer of the ejecta, whose composition was different, richer in freshly synthesized heavy nuclei, lanthanides among them, their presence written into the color of the light they produced. That color was a spectrum, and the spectrum held lines. Specific wavelengths absorbed more than others. In the months after the event, as astronomers worked through the data from multiple instruments, absorption features were identified whose pattern matched the predictions for strontium, an element sitting at atomic number 38, just below the boundary where ordinary stellar burning stops and the rapid neutron capture process takes over. Strontium was not the heaviest thing in the ejecta. It was one of the lightest things produced by the process that also built the heavier elements, the lanthanides, the actinides, and the atoms of gold and platinum and osmium that cooled and condensed as the cloud expanded and thinned over the weeks that followed. The process that built them is old in conception, proposed in a paper written in the late 1950s by 4 authors whose initials became its informal name, a paper that outlined, with remarkable clarity, the nucleosynthetic pathways by which stars could build the elements from hydrogen upward. The rapid neutron capture process, the R process, was among the pathways they described. In conditions of extreme neutron density, far beyond what ordinary stellar burning produces, even in the final seconds of a core collapse event, free neutrons can be absorbed by atomic nuclei faster than those nuclei can decay. An iron nucleus that captures a neutron becomes a heavier isotope of iron. If the neutron density is high enough, it captures another before it has time to shed the first, and another. The nucleus grows heavier, moving upward through the periodic table, not by fusing 2 nuclei together, but by adding neutrons, one at a time in rapid succession, building unstable, neutron-rich isotopes that eventually decay toward stability along the valley of stability, and in doing so can land at atomic numbers unreachable by any other route. The neutron density inside the ejecta of a neutron star merger is, for the moments it matters, among the highest in the observable universe. The material being launched outward is neutron star matter, matter in which the neutron fraction is near total, being decompressed from nuclear densities. As it expands and the pressure drops, the neutrons become free, available for capture. The timescale over which the R process operates in this environment is seconds to minutes before the ejecta have expanded and cooled to the point where the reactions cease. In those seconds, in a mass of material, perhaps 3 to 10 times the mass of the Earth, the entire upper half of the periodic table can be seeded from the elements just above iron through the lanthanides at the far right of that lower shelf, to the actinides, to lead and bismuth, and to the transient elements, even heavier, that exist only for moments. Gold sits at atomic number 79, platinum at 78, osmium at 76. These are not elements that any star can build through ordinary fusion. The binding energy per nucleon has been falling slowly since the iron peak, and adding protons to iron group nuclei by fusion requires energy rather than releasing it. The only path to gold from iron is through neutron capture and subsequent beta decay, which requires the neutron densities found in the collapse of a stellar core or the disruption of neutron star matter. The R process builds these nuclei efficiently, and the estimates drawn from GW 170817 suggest that something between 3 and 10 Earth masses of gold were forged in the event, not precisely known, because the conversion from the observed light to the underlying mass of specific elements requires models of the ejecta structure and opacity that carry their own uncertainties. But the order of magnitude is well founded, and it is large. 3 to 10 Earth masses of gold, created in 2 seconds, in the outskirts of a galaxy 130 million light-years away. A quiet collision of the smallest possible stellar remnants, carrying within its ejecta a library of elements that no supernova alone could assemble in quite the same proportions. The gold cooled as the cloud expanded. The atoms that had been neutrons, then unstable heavy nuclei, then the products of rapid beta decay, settled into the configurations of stable elements. Gold atoms with their familiar electron structure, platinum atoms, lead. In the weeks after GW 170817, that cooling, expanding cloud of freshly made heavy elements was the only place in the observable universe, at that moment, where new atoms of gold were being formed. Neutron star mergers are rare. In a galaxy the size of the Milky Way, the best current estimates suggest they occur perhaps once every 10,000 to 100,000 years. Numbers that carry wide uncertainty, but that are nonetheless far less frequent than core collapse supernovae, which occur roughly once every century per galaxy. The rarity is part of why the gold in the solar system accumulated over billions of years of galactic history rather than appearing all at once. Each merger event disperses its R process products into the surrounding interstellar gas. That gas is swept up into molecular clouds. Those clouds collapse under gravity into new generations of stars, carrying within them the inherited abundance patterns of all the deaths that came before. The carbon and oxygen of helium burning, the magnesium and silicon from massive star interiors, the iron from the radioactive decay chains of supernovae, and the gold and europium and neodymium from the rare ancient collisions of neutron stars. The oldest stars in the Milky Way carry a record of this enrichment history in their spectra. Very old, very metal-poor stars, stars that formed in the first billion years of the galaxy's life, from gas barely touched by earlier stellar deaths, show abundance patterns that reflect a different mix than the Sun does. Their iron content is low relative to hydrogen because the supernovae that preceded them had only just begun seeding the galaxy's iron inventory. But some of these ancient stars show elevated ratios of europium to iron, europium being an element produced almost entirely by the R process, and therefore a tracer of neutron star merger events. The scatter in europium abundance among metal-poor stars is wide, wider than the scatter in iron, or oxygen, or magnesium. This scatter reflects the rarity and the spatial patchiness of merger events. Each one enriched a small region of the early galaxy, and stars that formed near that enriched pocket carry more europium than stars that formed where no merger had yet occurred. The pattern is a map of ancient events written in the photospheres of stars still visible tonight. A spectrograph trained on a metal-poor star in the galactic halo splits its light into wavelengths, and shows the absorption lines of the elements in its outer layers, the chemical fingerprint of the gas from which it formed 10 or 12 billion years ago. In the position of the europium lines, in the depth and sharpness of those absorptions, is the memory of a neutron star merger that happened before the Sun was born, perhaps before the Milky Way had assembled its current spiral structure, in a fragment of gas that would eventually become part of the galaxy we live in. The Sun itself carries this history. Its photosphere, its composition, reflects the accumulated output of perhaps 10 billion years of stellar processing in the galaxy before it formed. The carbon in its atmosphere, the oxygen in its outer layers, the iron, the gold, all of it inherited from stars that lived and died in the billions of years between the formation of the Milky Way and the collapse of the molecular cloud that gave birth to the Sun and its planets. The gold in the solar system arrived already made. It was not forged here, it was gathered. The rocky planet that formed closest to the Sun, the third one outward, gathered its share. Iron dominated its interior as the planet differentiated, heavy metals sinking toward the center in the early molten phase, leaving a crust and mantle of silicate rock with trace quantities of everything the solar nebula contained, dispersed through the rock and eventually concentrated by the geological processes that followed. Gold, being dense and chemically particular, sank preferentially toward the core during differentiation, and most of the gold in Earth's interior is inaccessible, locked in iron and nickel, thousands of miles down, beyond any reach. The gold found in Earth's crust arrived later, carried in by the meteoritic bombardment that continued for hundreds of millions of years after the planet formed, or concentrated by hydrothermal processes that moved trace amounts through rock over geological time. Every gram of it came from space. Every ounce of gold in the crust traces its origin through the solar nebula, through the interstellar medium that the nebula condensed from, through the expanding ejecta of neutron star mergers that disperse their products into the gas of the early galaxy, through the millisecond violence of objects that had themselves spent millions of years spiraling toward each other across the dark. A gold ring is at its core a relic of a collision that happened long before the Sun existed, in a place that no longer exists in the same form, among objects that no longer exist at all. The objects that made it are gone. What they made is here. The elements heavier than iron do not arrive all from the same place or the same kind of event. Neutron star mergers contribute most of the heaviest ones, the lanthanides, the actinides, gold, platinum, but other pathways contribute at other mass ranges. The WAR process requires only extreme neutron density, and some fraction of core collapse supernovae may achieve the necessary conditions in particular regions of their ejecta, particularly in the neutrino-driven winds that blow off the surface of the newly formed neutron star in the seconds after the bounce. How much of the R process inventory of the galaxy comes from supernovae, and how much from mergers, is a question still being worked out, with the europium scatter in old stars pointing strongly toward mergers as the dominant source for the heaviest elements, while some intermediate R process contributions may come from other channels. The honest answer is that the split is not fully resolved, and the models that best reproduce the observed abundance patterns in stars of different ages and compositions continue to be tested against new measurements. What is not in question is that the two kinds of events are different and complementary, and that the periodic table, as it exists in any gram of matter in the solar system, is the product of both and of others. The carbon was made in stars too small to explode, shed gently from their outer layers as they became planetary nebulae. The oxygen came from massive stars burning helium in their cores, and from the same massive stars exploding and dispersing it. The iron came predominantly from Type 1a events, the detonations of white dwarfs in binary systems, releasing no compact remnant, producing vast quantities of iron group elements from a single event. And the gold came from the dark, slow in spiral of neutron stars circling each other for 100 million years or more until the space between them ran out. Each atom in a human body carries a different itinerary. The oxygen breathed in tonight entered this atmosphere from photosynthesis, but the oxygen atoms themselves, the nuclei at their centers, were forged in massive stars billions of years ago and dispersed when those stars exploded. The iron in the blood, the small quantities of gold, sometimes worn as jewelry, the calcium in bone, the sulfur in protein, each element takes a path through the history of stellar nucleosynthesis that leads back to specific conditions, specific temperatures, specific densities, specific kinds of stellar death. Not a simple path, and not a short one, but a path that can in principle be traced, step by step, from the present moment back to the interior of a star or the collision of its remnants, in an age when the galaxy was younger and the universe around it was smaller. The galaxy continues to process material. Massive stars form in molecular clouds and exhaust their hydrogen over millions of years and explode and seed their neighborhoods with the products of their interiors. White dwarfs in binary systems slowly accrete mass and occasionally detonate. Neutron star pairs, formed in the same binary system or captured later into mutual orbit, continue their long in spiral. The Milky Way will produce more supernovae. It will produce more kilonovae. In time, each event will add to the chemical inventory of the interstellar medium, raising the metallicity fractionally, adding new atoms to the pool from which future stars and planets will form. The process is not finished. It has no finish in any timescale that can be imagined restfully. It is simply continuing, a slow, steady enrichment, punctuated by rare, intense events, spread across a galaxy wide enough that the light from its far edge takes 100,000 years to cross. The molecular clouds that will form the next generation of stars are drifting now in the outer spiral arms, slowly cooling, accumulating mass as gravity pulls them together, carrying within their cold gas the inherited elemental output of everything that has already died. When those clouds eventually collapse and fragment into new stars, the stars will be born already enriched with more iron than the sun has, more heavy elements, a fuller complement of the periodic table assembled over the longer history that will by then have passed. Their planets, if they form, will have more gold in their composition than Earth does, in proportion. Their chemistry will begin from a richer starting point. A star being born now in the Carina Nebula, or in the Orion molecular cloud, is forming from gas that contains the dust of supernovae that exploded while the sun was already middle-aged, while the Cambrian was already past, while multicellular life on Earth had already diversified into most of the body plans it still uses. That star will burn for billions of years. Its planets, if it has them, will inherit the abundance patterns of every stellar death that preceded its formation. The gold in those worlds will carry, in its atomic number, in the binding energy of its nucleus, the record of neutron star mergers, some of which happened before the Milky Way finished assembling, in a universe still populated by the first generations of stars, massive and short-lived and brilliant. The first stars left almost nothing except the lightest elements they scattered when they died, and the heavier elements their explosions seeded into the primordial gas. The second generation of stars formed from that gas and burned a little richer, the third richer still, and so the process compounded, over 10 billion years, building the metallicity of the galaxy upward in a slow accumulation, star by star, explosion by explosion, merger by merger, each death making the next generation of matter slightly more complex, slightly more varied, slightly more capable of assembling into rocky planets and liquid water, and eventually chemistry complicated enough to look back at the stars and ask where it came from. The asking is recent. The process it traces is old. The oldest light in the universe carries no heavy elements in it. The spectrum of the cosmic microwave background holds only hydrogen and helium, the products of the first 3 minutes of nucleosynthesis in the early universe. Everything heavier than helium, everything above lithium on the periodic table, is the product of stars, of burning and of dying, of collapse and detonation and collision accumulated over the full span of cosmic time since the first stars ignited and then exploded in the first billion years. Every element heavier than iron is the product of extreme events, the cores of dying massive stars, the surfaces of accreting white dwarfs, the collisions of neutron star pairs in the outskirts of galaxies. It is a long history, and a violent one, but its violence is entirely in the past from the perspective of any single atom now resting quietly in a body, or a ring, or a stone. The quiet is the point. The violence produced the quiet. The supernovae and the kilonovae and the long inspiral of neutron stars are not aberrations in an otherwise peaceful cosmos. They are the mechanism by which the cosmos builds the material for everything that follows, including the peace. The carbon that makes the complex chemistry of life stable at room temperature came from stellar interiors. The calcium that makes bone rigid came from the oxygen-burning shells of massive stars.